Okay, he will have to pay more for the picture. So so years back, when was it? 2000, 2001. 2000, 2001. I was invited to Shahid Behishti in Tehran, in Iran, to give a series of lectures. And at that time, they never heard of modular function spaces, okay? And I gave them this series of lecture on modular function spaces. Now, the Iranian school on modular function spaces is by far one of the best in the world, yeah. So why am I telling you this? Not because of modular function spaces, no, no, no. I went there in December. It was December to January, during the break. And I don't know whether you know, Tehran is in the mountains, okay? And the university is on the mountain, so you have to, either you are lucky and you drive to the department, otherwise you will have to walk. How come that we can walk if we have roads? Because it snows. So the last day, this is all to come to the last day. The last day, it was snowing. I mean, snowing the night before. I was staying in the hotel in the city, of course. So when I woke up in the morning and I looked through the window, I saw snow everywhere, a lot of snow. I said, Alhamdulillah, today I'm not going to give a lecture. And then the guy who invited me, a mathematician from there, Behzad Jafari, he came to the hotel to pick me up. So I told him, but it's snowing. He said, yeah, in Iran we don't, can be snowing, no snow, it makes no difference. I said, okay, in my mind, wallahi, in my mind I said, for sure I'm gonna go and nobody will be there because it's a lot of snow. In fact, that's why the car did not drive. We had to walk up the mountain. Wallahi, it's a true story. I will never forget this. The room was full. Everybody was there. Everybody was there. So you guys reminded me that moment. So I'm so proud of you. Did you get the paper I sent to Javid yesterday? Bayon's paper? So quickly, who asked me yesterday? Who? Somebody asked me. Yeah, so there you can see about asymptotic normal structure property. I will talk about that in the tutorial today. It's very important to see the connection. Is a very profound problem in fixed point theory, which is in order for us to investigate the fixed point property for non-expansive mappings, of course, we need to have more information on the minimal set. So the minimal set, knowing something about the minimal set helps us to investigate fixed point property. As of now, the last known result on that one is the famous Karlovich lemma or Karlovich-Goebel lemma, 1975. So we're talking about 50 years. Nothing was done. It's a very hard problem. It's a very, very, very hard problem. And of course, the Karlovich lemma is the one that led to the asymptotic normal structure property. So I will be talking about this during the tutorial, okay? But that's not what his name, Lim. Do you see Lim? Yeah, yeah. Yeah. So Lim was more interested into proving common fixed point of a commuting family. Anyway, so shall we move? So now, do you expect me to teach you modular vector spaces in 1 hour and a half, 2 hours, when it's a book? Do you think that I will be able to do that? Do you think? What do you think? I'm asking you. I'm honestly asking you. What do you think? Do you think I will be able to do that? Ah, she said yes. Oh, why she's good. I mean, when somebody tells you yes, it means he believes in you. Huh? He believes in you. It's hard. You are going to pay more for the picture.
Sure. But today is discount. $1,000.
No, I will give you discount, but you're going to pay more.
Now discount is cancelled.
Discount is canceled. so, so I put it for you just to give you a sense that two things. Number one, it's not possible for me in 1 hour and a half, 2 hours, to be able to describe what this object is. And as I told you earlier, at Shahid Beheshti, it took me like 5 days teaching them about this. And they published a PDF file. I believe you have a copy of it. And of course, that was the seed for the Iranian School on Modular Function Spaces. It has a lot of stuff about, when I say modular function spaces, it has a lot about measure theory and so on and so forth. So this book was published recently, I think something like 15 or 19, I don't remember exactly. And I want you, I really want you not to ignore the concept of modular vector spaces. Now look at the difference. Modular function spaces, modular vector spaces. Okay? So what did we do so far in this class? First, or in these courses, lectures, we started with metric spaces and how to look at abstract structures, okay? And then I moved to Banach spaces, and now we are moving into modular vector spaces. Modular vector spaces is not just generalization, because since the advent of the internet in '94 with Netscape 1.0, people, for a reason I don't want to talk about now, is started to come up with anything to gain citations and improve the metrics. Okay? This is all due to this access to the data available digitally. But before 1994, especially in the 80s, late 80s, 80s, 70s, 60s, there was no digital data. So if you wanted to see something, you have to go and open a book, and there were some publications like Mathematical Reviews and Treblat that we don't hear anymore. That's it, it's done. They killed them. So this time, the people were not motivated by improving H-index, citations, and so on and so forth. There was no such thing as eyesight journal and so on and so forth, okay? So when modular vector spaces were done in the 50s by Nakano, it wasn't motivated by this kind of publicity or whatever. So I want you to grasp it. I really need you not to be blind on what's going on there, especially that it has major impact on PDEs, for example. My first colloquium talk, I'm so saddened that some of you did not attend, is about what's known as the energy, Dirichlet energy problem, which is connected to the P-Laplacian and modular function spaces, or what's known as variable exponent spaces. So what I will do today is an initiation. I will not teach you all the intricacies, okay? Yesterday I was very frustrated around midnight. I sent you the file around midnight. I was very frustrated because I couldn't put it small file. It was a long file. Okay, so shall we start? Yes? Okay. So remember, I'm going to give you the modular vector spaces, and modular function spaces are a special case of modular vector spaces. But modular function spaces were the origin of modular vector spaces. If you want to see the analogy, you have to go back to Banach spaces. Banach spaces were born with Banach in 1922, where he defined a vector with a norm. The concept of a norm is new, and as he did with metric spaces for the Banach contraction principle, he did it for vector spaces. He gave the norm properties of the norm, and then he said, he didn't call them Banach spaces, he called them class B, and he called them assuming that Cauchy sequences for the norm are convergent, which now we call completeness, okay? And so it was born in 1922, but we had all the classical, what they call classical Banach spaces, like L2 spaces and so on and so forth. They were known. It's not like weighted to, or C of K, which are the continuous functions on a compact set. So all this were known, okay? But they were not known as a norm, no. They were just known as vector spaces, function spaces, and with their classical. So here, so they are a generalization of what? Of normed vector spaces. So the module, and you will understand in a second why, the module is just something that generalizes norms. So you have norm is a module, and you have the concept of module more general, okay? Of course, more general in what sense? In the sense that it corresponds to a structure that may help us understand some of the intricacies that the norm cannot, okay, that the norm cannot. So now, where did it start? This idea of module, where? The seed, the original seed. It was in that famous paper by Orlich, 1931, okay? And what was the motivation of Orlich? Motivation of Orlich at that time was to come up with, construct Banach spaces that are not common, that are not classic. In fact, if you look at the books, the two volumes by Linder Strauss and Safriri on functional analysis, okay, very famous two volumes. They were supposed to have 4, but they got into a disagreement, and they only wrote 2. And these 2 volumes, they are called classical Banach spaces. One is about sequential Banach spaces, and the other volume is about classical Banach spaces. So they were interested to find or build new Banach spaces. And why is that? Why do we want to build new Banach spaces? In general, they wanted to build these new Banach spaces to respond or to answer questions that they were putting where. Does anybody remember where these questions were asked? Yeah, I mean, you know the answer. Come on. Uh-huh. I'm looking at your faces like, what? What is he asking? Anyone? You know the answer. Yalla. Okay, today is Friday. I'm going to be nice today. I'm not going to give you a hard time today. I'm not going to ask about the 2 words answer. So, anyway, it was in the famous Lvov school, Banach school. Remember? Huh? Remember the Scottish book? So some of the main beautiful results of functional analysis, like Anne Banach and so on and so forth. In fact, somebody who is maybe listening to us right now, send a question to Javid. His name is Mohammed Amin, by the way. And he asked a question about the Banach measure distance between Banach spaces. Okay, and we were having an exchange with Javid yesterday, and it was confusing to me, the question, and I wanted it to be confirmed, and I asked my AI assistant, yes or no? And I send you the answer, yes? So anyway, so the point is, most of the foundation of functional analysis goes back to that group with some big names there. So Orlich wanted to come up with a new space. So first natural reaction was, what is LP? LP is when you take the integral of absolute value of f of x to the power p dx, yes? So you have that p power, yeah, in the integral. Of course, the norm will be what? To the power 1 over p, fine. But what if I replace t to the power p, the power function, by another function with the same properties? Same properties. Look at my hand, okay? Increasing, convex, and so on and so forth. Equal to 0 at 0, and so on and so forth. So he came up with this idea, okay? So he said, now it's the integral of phi of absolute value of f of x dx. Yeah? So first. Now comes what? Comes, so this space is this one that you see right here, okay? And now comes what would be the norm, okay? Natural. You have a vector space. If you assume vector space, if you assume the condition that there is a constant lambda such that the integral of phi of absolute value of f of x over lambda, so you put lambda inside phi, then, or lambda time f, okay, for some lambda positive, this gives you a structure of vector space. Otherwise, it's not true, okay? The integral can be finite for f, can be finite for g, but when you put f plus g, it may be infinite. So to make it a vector space, you add that constant and it works, which you don't have in the case of p, because alpha will come out with alpha to the power p, and then you have no problem, okay? So anyway, so here is the norm in the case of LP. And now when you go to phi, there is a problem. Right there. 1931. What's known as Orlich spaces, okay? We have a problem. What is the norm? So the norm in the case of LP is just the integral to the power 1 over p. But in the case of this one, you need little bit to work, little bit harder. It's more complicated, and is not a direct norm like this one. 1931. Okay, 1931. Okay, so let's continue. So the connection between the integral and the norm, in the case of LP is easy. In the case here is complicated. I will give it to you, don't worry. Okay? But this point, that's what led Nakano to say, wait, there is more to the story. Not Orlich. So Orlich, he gave them a norm, and he showed them some nice properties of the norm, and that's it. But in the case of Nakano, he saw something more profound than the norm. Okay? More profound than the norm. So let's continue. So that's what I'm saying here by the work of Nakano, 1950. So we're talking about 31 to 1950, almost 19 years, 20 years before they saw, or somebody saw, that concept of module. Okay? The module was born with Nakano, not with the... Okay, so what is a module? So this was given to us by, what's his name? Nakano. Okay? So this is found with Nakano. So remember, all the work by the Polish school was more about functions. Now, what are the properties? And keep in mind, I forgot, keep in mind, just to help you, keep in mind that the definition that I'm going to show you, it follows this This is, of course, for what? Modular function spaces. Modular function spaces, because the vectors are functions. I wanted to keep this in mind, okay? But to give you the properties. But we are no longer, it's like what Banach did with the norm, okay, from the classical examples before him. Now we are looking at what Nakano is going to do, okay? Okay, so what are the properties? We have rho of x equal 0 if and only if x equals 0. Okay, you can, like we did for the norm, you have the semi-norm, semi-modular, and all this stuff. All this exists. I don't want to bother you with this, okay? So let's move on. Next, you have this condition. Now problems start to become a little bit what? Complicated. Right there. So first, we don't have homogeneity of the norm. Right there. You have what? Rho of alpha x, which means that rho of x and rho of minus x are the same because of the famous absolute value that you have there. Do you understand? But you don't have anything because phi cannot allow a constant to come out. You don't know what kind of function you have. Third one is true in general, but most of my work is done when rho is convex. And therefore, the condition number 3 is replaced by this condition. Do you understand? I'm assuming that phi is convex, as I told you. By replacing t to the power p, I'm assuming that. But in general, if you want to go more abstract, you don't need to assume what? Convexity. But I only work with convexity. All my work from the fixed point theory point of view, of course, not the modular point of view. And also, as you can see, I want you to see something very interesting. Okay? Let's take y equals 0 for the sake of it. Let's take y equals 0. Then rho of alpha x will be less than what? Alpha rho of x, because rho of 0 is 0. And if you let alpha goes to 0, this one will go to 0. So we are looking at some kind of what? Of continuity of rho. And the one that is important, the one that is really important, is this one, which is the left continuity at 1. Okay? Okay. Now, what is the space? Remember what I told you. If you take f and g in the modular, in Orly spaces, rho of f is finite, rho of g is finite, rho of f plus g may not be finite. Okay? So the space that we are working with is not the big space. So it's a space where we call it the modular vector space, which is the space where rho of alpha times x is finite for some alpha, You see it? So here, which is the same as this one, by the way. It's the same as this one. So we call it the modular vector space associated to rho. Okay? Associated to rho. Keep in mind, in the case of a norm, is the space, all of it, because norm of alpha x, alpha comes out. So, and also the norm is always finite. Module, no. Module can be infinite. If you wait a minute to go back, you see it? The module goes to 0 plus infinity included. So rho can be infinite. Now, there is one more property fundamental for modular vector spaces. I will mention it a little bit later, but let me say it right now, which is because of the lack of homogeneity, you have rho of x. Rho of x. What happened to rho of 2x? If you take rho of x over 2, just as an example, rho of x over 2 is less than rho of x. That's what you have there. I just showed you rho of alpha x less or equal than alpha rho of x. So rho of alpha x, alpha less than 1, is going to be bounded by rho of x. What happens if alpha is bigger than 1? Rho of 2x. It's the same, by the way, 2 or less. The problem is rho of x can be finite, rho of 2x can be what? Infinite. And it can be what? Non-controlled. So to be controlled, rho of 2x, controlled by rho of x, I will show you in a second what it means. This is called, is central for the people working in modular vector spaces or modular function spaces. Central. So this is known as the delta 2 condition. Now, you may ask me, delta 2, it can be any lambda, lambda bigger than 1. It's all the equivalent. Whether you have delta 2, delta 3, delta 4, but they all picked delta 2. All the people working in modular vector spaces or modular function spaces, they work with delta 2. But it's the same if you take any number bigger than 1. Any number bigger than 1. Anyway, of course, again, the beauty is to try to avoid delta 2. Because delta 2 makes working with modular vector spaces kind of easier. I didn't say piece of cake, no, but easier. Okay? So avoiding delta 2 will make a difference. There is a paper that a few mathematicians, I don't remember, I have it on my website, by the way, where they published a paper, and I had to what? Do a demonstration or proof that shows the same result without delta 2. And they called it the same title of their original paper, but I added without delta 2. Why I'm saying this? It shows you the importance for the people working in modular vector spaces or modular function spaces to try to work without delta 2. You will understand in a second why I'm saying all this. You will understand in a second. Okay, so what's the norm? The norm now. Okay, we need the norm. We have the vector space, what's known as modular vector space. Now we need a norm. Okay, so what is the norm? The norm is given to us by something called Minkowski functional. So it's a concept that existed before. Why am I saying this? Because of our friend Orlich. So when Orlich gave us Orlich function spaces or Orlich sequence spaces, vector spaces, he had a norm. He didn't wait for whom? For Nakano. Do you understand? And it was there where every time you have a special set, convex set that should be absorbent and so on and so forth, then you have a norm associated to the convex set where the convex set becomes the unit ball. So this is known. This is really something that was known before. And that's why here the properties of this set here, okay, which is convex because rho is convex, balanced because rho of minus x equal rho of x, and absorbance for any x you can find the lambda such that rho of lambda x is less than 1, etc., etc. Then you have this Minkowski functional, which is your norm but associated to CR. Now what happens if I replace R? In the case of norms, we have homogeneity, everything collapses. Do you understand? There is a relation between the ball centered at 0 with radius 1 and the ball centered at 0 with radius r. Do you understand? Because of homogeneity. But in the case of the module, we don't have homogeneity. So what happened to these norms? Okay, all of them. So they are all equivalent. And that's the relation you have right here. Okay? So these norms are equivalent. In this case, let us pick one of them because they are all equivalent. Let us pick one of them. And during the time of Orlich or even Nakano, they all took R equal 1. Okay? R equal 1. And they called it, they didn't call it Luxembourg norm. Okay? It wasn't called Luxembourg norm. Okay? It wasn't called Luxembourg norm. Luxembourg was a wonderful mathematician that when I arrived to California, Los Angeles, in 1987, I was visiting his regular seminar, and he's the one who found me the job in America. True story. I was just visiting America. I was trying to go back to France. And he's the one who pushed me to stay in America, and he found me the job in America. So why do we call it the Luxembourg norms? I know the guy, but why do we call it the Luxembourg norm? It's because he did with Zanin, very, very, you should find them. I think I have them as PDF, but I may not have. Beautiful 3 books, I mean, not books, 3 large publications on function spaces and everything about function spaces. Okay? He set the tone, everything that you want to know about function spaces. So, by respect to his work, they called that norm the Luxembourg norm, but it wasn't called Luxembourg norm early on. It was not. Okay, it should have been the Minkowski norm, but anyway. So, and you have these properties, the relationship between the norm and the module, the relationship between the norm and the module. Okay. So remember what I told you. This, what you see here, was known prior to Nakano. So it's very important to follow me here. Otherwise you get lost. I can lose you easy. You have to follow me. You're not going to find this written. What I'm telling you, I had to struggle to find it by myself. So you have to follow what I'm saying. This was known to our friend Orlich, okay, in the context of Orlich spaces, whether it's sequential or continuous with functions. Am I making myself clear? Including what? The norm, including the Luxembourg norm if you want. It was known. All this was known. The difference with Nakano, he put it in terms of modular vector space, in any vector space. That's what it is. Are you with me? Very important. Now, let's go to some examples. Okay? Some examples. So what are the examples? I'm going to go a little bit faster on this one. This is the Orlich function spaces. Yes? And that I mentioned earlier. But now I set up what? The stage of what kind of function we want, etc., etc. Okay? So let's move on. So this is what? The Orlich function space. And as you can see, look at it. This is the Luxembourg norm. This is up, what's his name? This is up to our friend Orlich, not to Nakano. Huh? Okay? So this was known. All this was known. And if you take phi of t equal t to the power p, then you end up having the classical LP spaces. Okay? LP spaces. Ah, I forgot. After this was published, okay, this was published, Mushilak and Orlich, once Nakano did his work. So, first, Orlich, nothing happened. People spend what? 19 years working on Orlich spaces. You have tons of publications on Orlich spaces. Okay? 1950, this famous work of Nakano on modular vector spaces. After that, Mushilak and Orlich, they came up with a beautiful example of not Orlich spaces, something else. I'll come back to this one. Very important. So let's continue. Yeah, so the next example I want to show you is the example of variable exponent spaces. Variable exponent spaces. A wonderful book. Up to few years before, I thought of it as the book. Now it's a piece of junk. Why? Because now I know what's going on. Once you know, at the beginning you are impressed by a book, and once you start to know the things, you say, wait a minute, this is not a good book. Very important, okay? So this book, I really consider it as the Bible for understanding variable exponent spaces. But now, knowing what I know, especially with our friend Osvaldo, this book is extremely bad. But for somebody who doesn't know, it's okay. I mean, you should have it, okay? It's available, huh? It's a PDF. And look at the title, Lebesgue and Sobolev spaces with variable exponents, okay? So let's continue. I have this book, by the way, if somebody's interested. Okay, so now what happened? You go back to 1931, okay? To that famous paper by Orlich. And there, I was telling the people during my colloquium talk, I had a visitor from Turkey, Nesreen, and she wanted to work with me for a year. She was doing her PhD in Turkey, and she wanted to work with me. So I was looking for a nice problem for her to go back fast on this story, and they saw something very interesting from this paper, okay? And what's interesting is that he took this example without this one, okay, 1 over Pn, okay? And he took it with the power n. So instead of to the power p, that was the classical little lp, now he made p variable. He put it equal n. Huh? So it's not an Orlish space. The problem is, I'm puzzled till today, he didn't do anything. He just gave it as an example. In the same paper in 1931, he gave it as an example, and then he moved on. He didn't even touch it. Okay. So why do we call it variable exponent spaces? Because the exponent is variable. If Pn is bigger than 1, of course we don't want Pn to be equal to infinity, yeah? But if Pn is bigger than 1, this module is convex. And it's really a module. It's very easy to see that you satisfy all the properties of a module, okay? Moreover, what? What do I want to say? Yeah, moreover, there are publications where you don't have 1 over Pn. Some, they have 1 over P of n, some do not. I'll explain. I don't think I'm going to explain here, because this has to do with PDEs and the Laplacian. So there is a reason, anyway. So you see, now, you see the rho star? In the rho star, there is no 1 over P. Okay? What's interesting, and this is not clear, what's interesting is that if you take, this is another module, if you take this module and the previous one, they give you the same space. The vector space is the same. Not the same constant that you are going to have for which rho of alpha x is finite. No. It's not the same constant, but still you are in the same. The vectors here and the vectors here are the same. And the Luxembourg norm for this one and for the other one are equivalent. Okay? So this one, this space, now we can look at as functions. What happens if I take the continuous variation of little lp, same as little lp and capital Lp? Do we have one? Yes, here it is. So you have it also in this case, where you have functions now measurable, blah, 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 all of it. And again, as I said, you have the same problem whether you have 1 over P of x or you don't have 1 over P of x, okay? And you have now the capital LP of omega, okay? And the book I showed you, they work with this, not with little lp, okay? The whole book is about PDEs and so on and so forth, therefore functions, and therefore they're working with what? Capital LPs. And as you saw, it has something to do with Sobolev spaces. So there is a definition to consider for the Sobolev what? Case. I don't think I put it, but we'll see. So as I said again, you have the rho star without the 1 over P, and then you have the same space, exactly the same as the other one, both, the same vector space, okay? And the norms are equivalent, the Luxembourg norms. But these two are different in some sense, Now, we're going to get into something very interesting, which is, look what I'm writing now. Rho P of this UN or UK goes to 0, but rho star P of UK does not go to 0. And here is the example. Okay, very simple example. It's going to get a little bit tricky now. We are talking about convergence in the sense of rho. Remember, rho is not what? You don't have homogeneity, and you don't have the triangle inequality. And if you remember at the beginning, I told you what happened if you don't have the triangle inequality. things get completely what? Messy. And if you are not careful, you are thinking in terms of what? I did tell you all this at the beginning. You are still thinking in terms of what? Distance. If you think in terms of distance, you are off. And it happened to people who published papers. Okay. And by the way, why they publish these papers? Because the reviewer is not good in modular function spaces or modular vector spaces. So here is an example of what is the Sobolev space I was referring to. So what you do, you have the derivative of the function, yeah? So think of it as one variable. Forget about several variables Rn, just on R, functions on R, you have the derivative, and the derivative also belongs to the LP space. So if the function belongs to LP, and the derivative belongs to LP, you have the Sobolev space W1, okay? And what you do, you define the module. Which module? This one, which is rho of u plus rho of the derivative, okay? If you have now more than one variable, so you have the gradient, and in order to define it, you have to take what? The module of the gradient, and the one that traditionally we take is the, or they take, not me, they take is the Euclidean norm of the gradient, okay? So just if you take the Euclidean norm, you end up having what? A function, real, and then you take the rho of that gradient. That's what they're doing, okay? And for a reason. It's not like they're doing it just for the sake of. Okay, so same. If you ignore the 1 over p, then you have another module, and the two modules are kind of equivalent in some sense. Luxembourg norms are equivalent. They define the same topology, and they define the same vector space. Okay, so it gets complicated in the sense that they become natural for defining what's known as the Dirichlet energy integral. The Dirichlet energy integral is this one. So the Dirichlet energy integral is this piece. And the problem is to find what? The infimum or the minimum of this integral for u belonging to a certain set. Okay? That's what I was talking about in the colloquium. Huh? So it's natural, that's what I want to say. Huh? And the 1 over p is important. If you don't put it, you get a different Laplacian. The regular Laplacian is when p of x is equal to 2. Okay, you get the Laplacian. But if p of x is not equal to 2, you get what's known as the p Laplacian. P Laplacian. Okay. So we have some examples. Uh-oh, what's going on? Oh. Now, we want to have some kind of convergence. Yes? So I already gave you a hint. Rho, if you remember, rho of uk goes to what? To 0. So from the beginning, when I got to know this with Kozlovsky, I was visiting California when I just arrived. Kozlovsky was, in fact, visiting under Fulbright scholarship. He was visiting Luxembourg. And the reason is because his work is a PhD, or what they call in Poland, the habilitation. It was on modular function spaces, okay? Modular function spaces with Mushilak, in fact. With Mushilak. So when he arrived to Caltech to visit Luxembourg, he started working. Caltech and USC, University of Southern California, are very close. One in Pasadena, the other one in Los Angeles, but very close. It's about 1 hour between the two. And he was working with Shimon, okay? Shimon Reich. And what they wanted to do is to start fixed point theory in modular function spaces. Start. So if you want to start fixed point theory in modular function spaces, the first theorem that you want to think of is Banach contraction principle. Okay? So to show you the divine intervention from heaven, Amin just arrived at that time to Los Angeles. Same time. They were working already. But when I arrived there, Shimon asked me, said, Amin, we are struggling, me and Wojtek, on this problem. Can you please help us out? And that's how I got initiated to modular function spaces. I told them I have no idea what is this. You explain to me, and I'll see what I can do. It's heavily dependent on measure theory. You can see the paper, the original paper. And as Izhar reminded me a few days ago about the Fatou lemma and the understanding of Fatou lemma for a student who is taking measure theory, and then the video I made online for it is, it gives you a sense of sometimes not understanding measure theory the way it should be, okay? We teach it, but we don't go beyond the surface, unfortunately. So anyway, so I got involved, okay? I got involved with them. And what are the ingredients that you need for Banach contraction principle? You have the iterates, and you want to show that the iterate what? Is Cauchy. Yes? But wait a minute, why do you need iterate Cauchy? You need to have it Cauchy so you can say through completeness that it does what? Converge. Okay. And then you want to show that the limit is what? A fixed point, and then show that you have only what? One fixed point. These are the ingredients, okay? So it is central to have what? Cauchy behavior with convergence. Convergence. You need to have that. So we need to define that. Wait a minute. Are we going to do it with respect to the norm? No. Why? Because it's done with the norm. It's done. Everything is done. So we are not working with what? With the norm. We want to work with the module. You see? So that's why from the beginning we needed to work with this. Now, was it us doing it? No. There is a famous book by Mushilak and is it Mushilak and Orlish or just Mushilak? I think it's only Mushilak. Lecture notes, old one, where he talks about this, and he inspires himself from the book or the notes by Nakano. Okay, so this was known. It's not like we came up with something new. So what is this modular convergence? Modular convergence. So we're motivated by all this, but we used what was known. Okay, so here it is. Okay, so you have the modular convergence, and you have the norm convergence. Do you see it? So we have the modular convergence, and we have the norm convergence. This was known. In other words, we just used what was out there. What's interesting, no. What is interesting is that if you converge in norm, you converge in the module. But you don't have this implies this, except if you have delta 2. Except if you have delta 2. If you have delta 2, the two convergences, they coincide. Oh, that's what I wrote right here. Okay? So if you have delta 2, the two convergences coincide. Otherwise, they are different. So keep in mind, if you have this one, you have this one. But if you have this one, you may not have this one. Okay. So now I'm talking about what? Delta 2. What are the properties of delta 2? There are many variants of delta 2. The one that is very common, that I like very much, is this one. Okay? Sometimes it is satisfied, sometimes it is not satisfied. Okay? So there are variants of delta 2. So this gives you a control of rho of 2x compared to rho of x. That's what it means. Rho of 2x over rho of x is bounded, okay, above. Now, if you go back to the case of variable exponent spaces, this is true in any vector, modular vector space, okay? But in the case of modular exponent spaces, variable exponent spaces, this is equivalent to the one I told you before. This one. This one. This is if and only if this. But not in any modular vector space. That's not true. Okay? That's not true. Anyway, and one more thing, there are two numbers in any paper written on variable exponent spaces. You are going to see two numbers, whether it's sequential or continuous. You are going to see these two numbers, p minus p plus. Okay, p minus p plus. So p plus, if it's finite, you have delta 2. Why is that? Because what is rho? Rho is going to be the integral over 1 p of x, absolute value u of x to the power p of x. But if p of x is bounded, and if I put a 2 inside, the 2 comes out with the plus. And the k you generated using what? The p plus. Are you with me now? You see it? So remember, our p of x are all between 1 and infinity. Yeah? That's why. Okay? So it holds if and only if. Huh? Okay. A little bit more about topology. Huh? So now we have convergence. Yes? So when I was doing this paper with Shimon and Kozlovsky, that's what we did. We just did what? The convergence. Okay? Now, to take them, that was Banach contraction principle, and you will see it. But to take them to what? The next level. They are now listening. They are only helping me with the modular function spaces. To take them to the next level. What is next level? From Banach contraction principle. What is the next level? Huh? Wallahi, I didn't hear you. Excuse me. No. No. Huh? Who is talking? Yes. What's that? No. You know the answer. What happened? We have Banach contraction principle. What is the next big thing? No. No. I mean, I love you guys. Wallahi, I love you. My students, when I ask them this kind of questions, they start telling me all the answers. I tell them, okay, let's open the book and start saying all the words. You know what? We'll hate it. Sooner or later, we'll hate it. It's 1965. Come on. So it's to go from contraction to what? Thank you. So if you go to non-expensive, or Kirk-Fixed-point theorem, you need normal structure property. And normal structure property, the convex can behave very badly. And I know how to avoid that, not to work with the convex sets. Using what? Convexity structures. People did not know this. They never heard of this. So my point is, I will mention it at the end. I called it the compactness in the sense of balls, but this is the reason why. I mean, without putting it, because I couldn't put it. But anyway, so these balls, I needed them for that reason. Only for that reason, for non-expensive mapping, I needed the balls. And specifically, the closed ball. They are not closed, nor that they are open. But we preserved the same wording definition as the metric case. Yes? Are you with me? Now, this was done in 1988. A year ago, I started working. We went back to this that you see there, and myself, Osvaldo, and two Czech. One of them is in the US, in Ohio. His name is GIAN. And the other one is Alex in Czech Republic. And we finished the paper. But what happened, this is the first time it happened to me in my career, that one of the authors died. So we were like this. What to do now? Okay, it was Alex in the Czech Republic. He passed away. And the paper, we're going to submit it now. I mean, now. But it's a paper, I had to make a stop because we arrived to 40 pages. And they said we have to cut because it's too big. But it's mostly about what? Topology of modular vector spaces. You see? Topology of vector space. So it wasn't done before. And there is a motivation why, a reason why. Oh, let's continue. So it's not known. That's why I want to say the word is topology, but don't pay attention too much to the word. It's just seeds. We are not there yet. Okay. So anyway, all this is coming from this paper, by the way. And also before, what we did is set is row closed because I needed that for the Banach contraction principle. Row closed if and only if row convergent, the limit belongs what? To the set. Okay, we needed that. We did not see it from what? Topology point of view, but we put it as a definition. Yeah. So for example, the balls are row closed if and only if row satisfies the Fatou lemma. So the Fatou lemma, if and only if you have the Fatou property, if and only if the row balls are closed. I'll give it to you, don't worry about it. So anyway, so this is just the beginning. As you can see, property I, we used it in 1988. But we did not know that it was a topology. We just used it, okay? Okay, so the Fatou property. If xn converges to x in the row sense, then you have row of x minus y less or equal than the limit. This property is known in modular function space. It was known prior to Nakano. It was known. And to help you out, if you have the case of Orlich continuous functions, capital L phi, then what you have there, instead of row convergence, because there is a subsequence such that converges in measure, then you have the classical Fatou lemma with the measure. Do you understand what I'm trying to say? So there is a connection from the work of Orlich. But they kept it what? In modular vector spaces. They kept it in modular vector spaces. Okay? And this property holds if and only if the balls are row closed. The balls are row closed, meaning that if xn converges to x in the sense of row, x belongs to the ball as well. The xn's are coming from the ball. Now, as we did, when I wanted to go from Banach contraction principle to Kirch's fixed point theorem, 1988, I needed what? But I needed the geometry, because the Kirch's fixed point theorem says what? That you need normal structure property, which is a geometric property. And in fact, we don't know that property very well. What we know is that if you are uniformly convex, or uniformly convex in every direction, then you have the normal structure property. People focused on the geometry part, it implies the normal structure property. But it's not easy to work with the normal structure property. It's a very complicated property, extremely complicated. In fact, that's why James' example, the renorming of little l2, was wow, okay, for them. Okay, so now, what is strict convexity for rho? What you see there is similar to the norm. If you replace rho by the norm, you get same definition, exactly the same definition, okay? So what comes next? Uniformly convex in every direction. So you have the definition similar to what I gave you yesterday. And if you remember carefully, because I was thinking about today, is that I gave you a definition that is not classical of UC. It's equivalent, but not classical. And the reason why, because this definition can be adapted in metric or non-linear, okay? So now, what is the classical one? But to understand the classical one, the direction in this case is going to be z1 minus z2. You have 2 points, and the direction is this one. Do you understand? When we say uniform convexity in every direction, what is the direction? It's z1 minus z2. It's this one here. You have the vector z1 and z2, and this is the direction, okay? So if z1 is different from z2, this vector is not equal to 0. Yes? Okay? So if you put h equals z1 minus z2, it becomes what? Y is x minus z1, and x minus z2 is y plus h. So this, the norm of this one will be less than r. the norm of this one will be less than r, and the norm of this one will be less than 1 minus delta times r. Okay? So this, you see this with this and this is the classical what? You see, the classical definition of uniformly convex in every direction that I started with in 1983 in Zisler's paper, okay? The first paper I read in my career, that is the definition. That is exactly the definition. But this definition is not adapted to matrix spaces. Why? Because what does it mean, y plus h, if you are in cut zero spaces? I have the middle point, but what is the sum of 2 points? Yes? Do you see the problem? And the same goes here. What is y plus h over 2? So this is not adapted definition to nonlinear what? Cases. Okay. So now you have this definition, the classical one. And what I just told you is exactly what you read here, including what? Cut zero spaces, which is a wonderful example where we can talk about, you see it, but using the other definition, not the one, the traditional one, the classical, which are equivalent in the case of linear stuff. So now, what's the relationship between UCID and SC? If you are UCID, you are SC. Okay? You are. But of course, if you are SC, you are not UCID. That's the case of linear, because rho can be a norm. The modular can be a norm. So no, there is no hope that they will be equivalent. They will be equivalent. In general. So if you have UCID, then obviously the Chebyshev center that we have to define will have at most what? 1 point. Remember I explained this to you. So that's how we get what? The normal structure property. We may need some compactness. Why? Because we need the Chebyshev center not to be what? Empty. Because why? The minimal set. So I need tools to prove the existence of a minimal set. Therefore, I need some kind of compactness. Once I have the minimal set, I need to show that the minimal set is what? Diametral. Like what's happened with Kirk. So we had to establish A and B. Do you remember A and B for the minimal set? Anyway, so A and B, we have to establish it. Once we have it, the B tells me what? Because he needs A. The B tells me what? It tells me that set is diametral. And if the set is diametral, normal structure property forces the set to be reduced to 1 point. Once it's reduced to 1 point, it is a fixed point. You see how it fits? And the same goes for the third property, which is Karlovich lemma. What Bayon did, he just said, I want it to fail Karlovich lemma, and therefore he came up with the concept of what? Of asymptotic normal structure property. So if we know more about the minimal, I assure you will become star in the community of fixed point theory. You will become star if you can find anything new about the minimal set. Don't waste your time on this. It's too complicated. But in case you are coming up with anything to help us understand more the minimal sets, then wow. So anyway, so this is a paper where what I did, there are 2 papers. They came at the same time, okay? First one, working with Shimon and Kozlowski, or Wojtek, about establishing Banach contraction principle at the beginning of fixed point theory for non-expensive mapping. That was the first one. Second one, I said, okay, fine. I mean, this is just, putting the assumptions, the hypothesis to make it work. I need concrete examples. Again, the divine intervention. At the same time, this Chinese mathematician was visiting Northwich. So you have Chen Shutao, Amin, Shimon, Kozlowski, all at the same time. At the same time, if I delayed my PhD just 6 months, I wouldn't have met these people. And by the way, even my trip to California was done because the chairman is a big name in fixed point theory, close friend to Bayon, Ronald Bruck. He came to Paris, and he was asked by Bayon to be in the committee of my PhD. And when I finished, he said, do you want to visit us for a year? That's how it happened. Why am I telling you all this? sometimes, and that was my colloquium, which is the accident in life, okay, my first encounter, second encounter, third encounter, and fourth one, is that in your life you meet some people that will take you into a different route that can be very rich if you accept to communicate and listen. So now let's go back to Chen. I put Chen Shutao, I put Aimé Kamsi, I put W. Kozlowski, and I put Chen Shutao. And the reason why I put Chen Shutao, because I found out later on that in some of his papers it's S. Chen, and in some of his papers C. Chen Shutao. I mean Chutao, sorry, C. Chutao. So I am completely lost to whether he's Chen first name or Chutao first name. And he's in Harbin University. He has an amazing story. I will not tell you about it now, why he got interested in this. But what's interesting, he was an expert. I mean, Polish people, they love the guy, okay? There is a story, a beautiful story, but let's move on. And he is good. He's very good at Orlish spaces. Ask him. So we said, okay, me and Kozlowski, we went to see him in Northridge, and we say, Chen, we have this problem. We have this property, okay? And we want to see if you can come up with some characterization in Orlish spaces, okay? But we don't want delta 2. That was the condition. Can you help us? Why? Because Kaminska showed that if you have delta 2, the norm satisfies the same properties. It's really back to the norm. We don't want that. We want to show the people that the norm is bad and the module is rich in the case of delta 2. We have some kind of originality, okay? And he said, okay, fine. So first example he did two examples. First one is when phi, the function that gives you the Orlish modular, okay, the function phi, if it's strictly convex, so they have this concept. This is well known. So in the classical theory, if phi is strictly convex and delta 2, phi satisfies delta 2, then you have the norm, which is strictly convex, and you see they are equivalent. Now we told him we don't want delta 2. He said, okay, if you don't have delta 2, and we don't want it for the norm, which is very complicated, we want it for the module, because we are working with the module, he gave us this theorem, beautiful, okay, which is this one that you see here. And what's amazing is that UC and SC, I mean UC, just UC, don't worry about it, and SC are equivalent, which is not the case for norm in vector spaces, in the classical norm, in just normal norm, okay? The proof is very technical, very technical. Okay, so this is Kaminska's result with delta 2. See it? If it's strictly convex and satisfies delta 2, then the 3 also, for the norm, okay? Now, this, I wanted to show it to you to explain what's happening now with uniform convexity. I showed it to the people. So this goes to Clarkson, okay? 1936. So Clarkson used this inequality to show that capital LP is uniformly convex. I talked about it, okay? And in the case of capital LP, there is no need to worry about modular because the module is exactly the norm up to a certain power 1 over p, okay? They are the same. So where did he get this inequality? From the, I told you about it, from the parallelogram identity. And how do we see now the proof, as I did for Hilbert? You get it from this term. If this is bigger than epsilon, okay, this one, then you're going to have this one less than 1, 1, half 1 plus 1, 1 minus this one. This one is what it gives you the delta of epsilon. You understand? This term, this one, fundamental. Now what happened for variable exponent spaces? I wanted to pay attention to this. What happened when p goes to infinity? Then the 2 comes out. It becomes what? 2 to the power what? P. And if P goes to infinity, in the case of variable exponent spaces, this is exactly to avoid to have or not to have delta 2. If I don't want delta 2, I know P will go to what? To infinity. And if P goes to infinity, what happened to this term? What happened to this term? Once I take the 2 out, what happened? It goes to where? And if it goes to 0, I lose what? The uniform convexity. Early on, 1988, I said, wait. Why are we taking 2 out? So I suggested, at that time, no. Let us keep the 2 inside. Don't take it out. But in this case, instead of having the norm of x minus y in the definition of uniform convexity, it becomes what? The norm of x minus y over 2. Inside. Norm is homogeneous, makes no difference. But for the rho, it makes a difference. Early on, I asked this. 1 with the 2 inside, 1 without the 2 inside. I call this one UC1, and they call this one UC2. So it's a new uniform convexity. What did I ask our friend Chen? I asked him with the UC2. Can you give me an example with UC2? That was not known before. It was not known. And of course, on the top of that, I don't want delta 2. So anyway, this is when P is between 1 and 2. This is the inequality. It was discovered later on, okay? Our friend, what's his name, Clarkson, to prove LP with P between 1 and 2 is the uniformly convex. He used some heavy tools. But this is very important for the people working in, look at this one. This is the famous what? Variable exponent sequence space. Okay? So it was done by Sandy Rasan. This is beautiful inequality that I worked a lot on. So here we have this result, okay, for little LP. Okay, let's move on. Now, of course, sorry, I forgot. This is not Orlich. Now we're talking about variable exponent spaces, okay? Variable exponent spaces. You have something for the capital LP, same, strictly convex and so on and so on. Same example, okay? And I want to show you this. This is a technical lemma where rho of u is less than r, rho of u is less than r, rho of u minus v over what? 2 inside, bigger than epsilon r, yes? Huh? You have this. So it's like 1 minus delta times r. But what I put in red is to show you that the delta does not depend on r. In the general definition, there is an r in the delta. But when we do calculations for variable exponent spaces, we did not find r. It's very important for the proofs, the technical proofs that we are looking for. I mean, we can work with r or without r. So that's why I said you have this and this. But in fact, this one implies this one. But they are the same now because the delta does not depend on r. Let's move on. Here we have what? Modular uniform convexity. I'm done with strict convexity. I'm done with what? With UC, and now I'm going to uniform convexity. Remember all this, I'm keeping an eye on 1965. Yes? All this, okay? So here we have what? The definition. As you can see, rho of x minus y. Rho of x minus y, it means I'm dealing with UC1 or UC2? Which one? UC1. So that's why I called it here UC1. Are you with me? So if I go to the next one, oh, and we have this property. I saw it in that famous book I told you about. Similar, but it's different, slightly different. So I called it UC1 star. Okay, so look at this one now. Look what happened here. So we have the 2 inside. This was not known. If you look at the books on modular geometry, you don't see this one, you see UC1. So of course, if you have delta 2, the 2 are the same. If you have delta 2, if you don't have delta 2, they are different. Why? UC1 comes from usually bounded P, and this one can be for unbounded P, okay? Which allowed us to solve a problem that was 50 years old recently. So it's a really beautiful property on this, with the 2 inside. And we have the UC2 star, the same, by putting, instead of having rho of u minus v, we have now rho of u minus v over 2, okay? Okay. So this connects, for example, Orlich. So same examples. We have Orlich, variable exponent spaces. Orlich, we have this definition of very convex. I had no idea this definition existed. It was Chen who did it. Chen said, this is the definition of very convex function, and from there we proved something. So now, do we have an example? Always. Do we have an example of a very convex function and which does not satisfy delta 2? For Orlich, I'm talking about. And they give us these 2 examples. Okay? They are very convex, but they fail delta 2. So now what do we have? Very convex is equivalent to UC2 for the rho, of course. What if I throw in delta 2 here? Then it becomes the norm. You understand? Is uniformly convex. And this is the, again, same paper where this is done without delta 2. Okay. Now, let's go to the variable exponent spaces. What's going on? Variable exponent spaces. We want p minus to be bigger than 1. Why? Because if p minus is equal to 1 on a set of measure non-zero, take functions where the support is only on that set. So I have the variable exponent space. And take a set of measure non-zero where the function is equal to 1. Okay? Then on that set, and I take functions only with support in that set, 0 everywhere, but only on that set. You will find a copy of L1 inside your space. A copy of L1 inside your space. And copy of L1, it fails all the geometric properties. So all the geometric properties are bad. No straight convexity, no nothing. Okay? And the same goes for L infinity. Okay? So we don't want this to happen. That's why we have that assumption that the essential env is bigger than 1. We want to avoid not to be equal to 1. And we have now the module with 1 over p of x. So we have UC2 star, which implies UC2. Now we go to fixed point now. Now I just gave you, I missed a lot because I couldn't, okay? So now let's go to fixed point now. Now let's start looking at fixed point in modular sense. So first of all, we're looking at functions which are Lipschitzian in the sense of the module, not in the sense of the norm, because what's the point? In the sense of the norm. So we have what's known as a modular contraction. Okay? You will find papers out there where they put a lambda here. Okay? There are some authors. They do that. Wrongly, of course. But especially the guy who did modular metric spaces, he put a lambda and he wanted to agree. Okay, we assume that always X is row complete. It's like, you know, when you have the Banach a vector space, it's the same. It's very, very similar. Vector space, a norm, is not necessarily what completes. So it's the completion that will hold with the norm. So the Banach space is not the original vector space. Does it make sense what I'm saying? Do you remember this business? So you take R to the power this. You know what's this, yes? sequences which are eventually zero, okay? And you define that completion, and therefore it's row complete, and row closed will make the limit Cauchy's converges in X row, but the limit will belong to C because it's row closed, just to explain a little bit the intricacies of the topology. Now, row bounded is new. You see it now. We have no ways of how to eliminate that. We don't know. This is 1988. We don't know. Honestly, we don't know. We need a different proof altogether. And then we have what? The row of convergent. We have one fixed point. Yeah? So this gives you what? Banach contraction principle, the first one that Shimon and Kozlowski were working on. I just joined the team. Okay? And they had some very struggle with this theorem, and we started to get moving. They were functions, not modular vectors. Now, what about charisma? So, in the case of Banach contraction principle, you guys have no problem, yes? Because it's easy, just, the iteration. Okay, we have a problem, as I showed you, kill it by taking boundedness, and you're okay. What about charisma? Charisma, you cannot avoid it. After what I did, you start to see the inside working. Why? Because you need a triangle inequality. How are you going to have a partial order? So in the proof, remember the Kirk's problem. Without the additivity or the triangle inequality of rho, you get stuck, really stuck. And in fact, it fails. Because I told you about the square. Yes, the original problem of Kirk is false. And rho can be a square. Yeah, can be. In other words, d squared is a module, the norm squared. Norm squared is a module. So now we go to what? After we are done with contractions, we go to non-expensive. But as you can imagine, we did not do just this. We did a lot of things. Like what? Like asymptotic non-expensive mappings, semi-groups, and so on and so on. We did a lot. That's why you have the book. It's not just this. But I want to give you a feeling of how it started. Really a feeling. Putting what? An analogy between what we did between Banach contraction principle, Kharisti fixed point theorem, and 1965, and modular vector space. I wanted to show you the parallel between the two. And if you don't pay attention to 1965, your research will stop with the theorem I just showed you. You will stop there. But because you know 1965 and beyond, now you can continue the research. Do you understand? Okay, so here is now a rho non-expensive. But for rho non-expensive, you cannot escape it, because a norm is a module. You have to go back to the theorem of Kirk and see all the ingredients that you need. But the ingredients are normal structure property and some kind of compactness. Convexity, I have it. Rho is convex and domain is convex. Okay? The other one, no. The other one, I didn't. You see it? C is not convex. It's very, very close to what's going on in what? In the case of classical fixed point theorems. But in the next case, we are going to assume that C is what? Convex. Subtleties that you have to pay attention to. Question. Non-expensive for the module. What about non-expensive for the norm? Is there a relation? Luxembourg norm. Is there a relation between this and this? Lipschitzian with respect to the module, Lipschitzian with respect to the norm. Okay? All this, we started right there to ask these questions to understand what's going on. We don't want to build something that is obvious. That is the first result. Now, if you have rho of lambda less or equal than rho of lambda, then it is non-expensive for the norm. Now, this answers the crazy guy who gave me a hard time. He wants to put the lambda, his name is Chishyakov, and he came up with the concept of modular metric spaces, and he put the lambda. Once you put the lambda there, then there is no sense of talking about non-expensive for the module. In fact, it is non-expensive for the norm. in his case for the distance, okay, the Luxembourg distance. So I told him, you should not. You should only do it for lambda equal what? 1. Don't do it for any lambda, okay? Some people fell for that. Not only him, some people fell for that. They put for every lambda, and in fact, why? Because they wanted to be what? Non-expensive for the Luxembourg norm. But once you are for the Luxembourg norm, use what? Classical theory, and you are dead. Right there. It's not interesting. So the question is, do we have an example where it is non-expensive for lambda equal 1, but not for any lambda? Meaning what? It is non-expensive for lambda equal 1, but not for the norm, yes? So this way, the two classes are different. Okay. Here is the example. Okay. This was done 1988 in that famous paper with Shimon and Wojtek. What's interesting, I did not know this because I was new. I was just initiated to modular function spaces. In fact, in that example, which was published in 1989, in that paper, what we use is, we called it Mushilak-Orlish space, but in fact, is a variable exponent space. Do you see it? It's a variable exponent space. So look at it. You see? This is your P of x. We did not know. I did not know. And nor that what his name, Shimon. And of course, Shimon did not know anything about this. But also Wojtek, who is coming from Poland. Okay? So here is the example. And what you see here is that the norm, it's linear. T is linear. So T of 0 is 0. But the norm of T of f is strictly bigger than norm of f for this f, the indicator function of 0, 1. Anyway, but let's move on. So the two classes, we're very happy. Why? Because the two classes are different. So it's meaningful to investigate non-expensive mapping for the modular. It was meaningful. Oh, by the way, let's go back. Sorry. Pay attention. What is the supremum of P of x? I did not know this at that time. Now I know. What is the supremum? What is x? What's the omega? Omega is what? 0 what? Plus infinity. Therefore, what is the, and P of x is equal to what? X plus 1. Therefore, what is P plus? The supremum of P of x. What is it? Obviously, what is it? Yeah, it's infinity. So, for sure, 100%, we fail what? Delta 2. So here, for this module, we don't have delta 2. Okay, let's continue. Now, here is the theorem. So we start now. First, uniform convexity. If we have uniform convexity, we have fixed point. That is Browder and Goer, yes? So we have it. This goes back to 1988 paper, the original one, okay? So you need UC1 and you are okay. You have everything nice. And we use almost the same ingredient as Goer. Same ingredient as Goer, not Browder, but we call this Browder-Goer modular version, okay? Now we go to Kirk now. Huh? So for Kirk, we need what? We need normal what? Structure property. So from 1988, I set up the stage, which is what? The Chebyshev quantities, Chebyshev radius, center, all this, with respect to what? To the module. With respect to the module. And you have to be careful. Why? Because in the case of Banach, what did they show you? This is the Chebyshev center, huh? Yes? R of C is less than delta of C, the diameter. That stays the same. What you don't have now is this one. This, you don't have it. Why? Because this is based on the triangle inequality. So for example, to show you this, you have distance from x to y, less or equal than distance of x to z plus distance from z to y. This is less than r of zc plus r of zc, which is twice divided by 2, and you take the infimum, and you will find half of the diameter less than what? Because this is for every x and y, and that's how you get this from the triangle inequality. Without triangle inequality, you don't have that, period. What's happening with the module? Don't ask me. Now, we have UC. If you remember, not all the time, in the case of Orlich, in the case of variable exponents, I showed you that UC and SC, strict convexity, are equivalent. Okay, you have UC. What does UC says? It's true that the Chebyshev center has at most one element. True. So if you have one element, you will have normal structure property. What is the problem? Is that the Chebyshev center can be what? Empty. So how do you avoid emptiness? You need compactness. In the case of Banach spaces, reflexivity, weak compactness. In the case of modular, what is the weak compactness? Weak compactness will come from what? From the dual. We don't know the dual. We're working on it right now, me and Osvaldo and Jan, in this paper that I told you about. We don't know what's the dual. They have some kind of ideas, but no, we don't have weak topology for the module, except, of course, if you go through what? Through the Luxembourg norm. But we don't for the modular sense. And therefore, you have to come up with what? With different type of compactness. And that's where Maurice Pouzet and the work I did with him helped me understand this prior to what? To visiting California. So when I came to California, I thought, oh, I know how to do this without doing what? Weak compactness. So I used balls and what's known as admissible sets. Do you understand? I learned it from where? From my contacts with Maurice Pouzet, as a student, of course. And we have now this theorem. Of course, it's in the same paper, but they couldn't grasp it. I'm talking about Shimon and Kozlowski or Wojtek. They couldn't grasp it. I brought with me this knowledge, and we implemented. And so I called it yesterday for the first time, because I didn't want to bother you with this. It's too technical. So I called it raw ball compactness, but it's not. It's not called raw ball compactness. I just invented this yesterday. So don't believe if you go and say, oh, Dr. Amin, or whatever you call me, and oh, he said raw ball compactness, and you start looking, you are not going to find raw ball compactness. There is no such thing as raw ball compactness. Okay? Any question? I swear, I thought I'm not going to be able to do it within the time allocated. And I had to cut so much because I said if I do it, it's going to be the whole day, and we cannot. It's enough for you to see me for 1 hour and a half. The whole day is too much. Anyway, any question? So this afternoon during the tutorial, I really want to touch on that point because I felt bad I didn't talk about it. I'm talking about Karlovich lemma. So I will touch on it during the tutorial, and that's it. And I will be done. Okay? Thank you.
Okay, thank you very much. So now a tea break for 20 minutes. So tea is ready. So let us join the tea, and after tea there is a talk by Professor B.C. Dadi. So application of fixed point Okay. So we have to stop by 12:45.
Good morning to all. So to begin with, I am thankful to Professor Javed Ali and his team for inviting me for this GIAN program. So I will speak on this topic: two basic topo-analytic Habib-Fishburne theorems and non-linear differential equation. So I hope all of you are aware of the fact that most of the dynamic systems, they are not linear. Straightforward. Complicated means they are non-linear in nature. So first, French mathematicians Henry Poincaré first recognized the importance of such type of equations, non-linear equations, and he predicted that future mathematics would deal with only non-linear equations. So this is very difficult to deal with non-linear equations. Even if there is a simple non-linear equation, it is not possible to solve it. So different approaches by different mathematicians have developed. So one is say there are different differential inequality. Another one approximation theory, approximation method. Third one is that numerical methods. Fourth one say function analysis method, and so on. Different approaches are there. So nonlinear operator theory from the subject of nonlinear function analysis. This is the famous Picard iteration method. So its proof is lengthy, quite lengthy, 2-3 pages, and involve many more analysis. So then what the Banach did? Remember, Banach it is not his own theorem. He borrowed the idea from this Picard. He just extended the idea of Picard to abstract setting in the metric space. That's all. Same with same proof, same method, everything is same. But it has become more popular. The Banach quantization mapping principle. Basic idea is of Picard. He just extended that idea to metric spaces. What is the advantage? So advantage is that in if you apply Banach quantization mapping principle, within 2-3 steps you will get the solution, unique solution, and the same conclusion. Sequence of successive approximation goes to the solution, that unique solution. 2-3 steps. This is the advantage of that. One more advantage is there. So in Picard iteration method, it is assumed that LA is less than 1. Then it becomes quantization. But if you apply Banach quantization principle, there is no need. For any Lipschitz condition, it works. I have one paper proved in this. Lipschitz condition. It is proved in Indian Journal of Pure and Applied Maths in 1997. So in that paper, this condition is relaxed. It is redundant. I applied Banach quantization principle, but no condition on the Lipschitz constant. How it is done? Actually renorming of the space. I have renormed that space, equivalent norm. Another norm is defined, which is equivalent to previous norm, and then shown it is Banach quantization. And without making any assumption on this Lipschitz constant, we get the unique solution. So this is the advantage of Banach quantization mapping principle. How it is done now? How Banach quantization principle is applied? Very simple. So 2-3 steps. Very simple. How to apply Banach quantization principle to differential equation, non-linear differential equation. So first of all, it requires a little skill. Remember, problem is given, okay? Differential equation is given. You first of all find what about its solution. You will write the definition of the solution, where it belongs, where the solution belongs to which function space. You try to find the function space, appropriate function space, and then you place this problem into that function space. So generally here we assume continuous. So space of continuous and bounded continuous function, real value continuous function on J, closed interval J, CGR. Here we have placed this problem into this place. This is the proper space. So you first of all you place your problem into a particular space, abstract space. Then we can apply. So metric space is not a linear space. It is non-linear space. So metric space cannot be considered for application at all. So you have to always consider a linear space for the application. So we consider this linear space. It is Banach space with supremum norm. And it is Banach space. So, this function is taken for the study, appropriate function space, and you place this problem into this space, and this norm generates a metric. So, it is compared with respect to that metric. So, it becomes a Banach space. So, this is first step of application. What is the first step of application? You find a appropriate function space for the solution, and you place that problem in that function space. Okay. So, then second step is very simple. Function is continuous, it is integrable. Function is continuous, therefore it is, so we consider only Riemann integration, not Lebesgue or any other integration, only, so it is integrable, Riemann integrable. Okay. Then you just integrate both sides using the theory of calculus. You apply the fundamental theorem of calculus. What is the fundamental theorem? You know, might be knowing all of you. What is the fundamental theorem of calculus? So, we apply fundamental theorem of calculus on this. So, what do you get here? Like this. Here, this side you apply. It exists because function is continuous. Therefore, it is integrable. So, this integral exists. The second step. This is the second step. You convert, and what is the left hand side? Just you will get here like this. This is the second step. You make use of calculus, using the theory of calculus, using the fundamental theorem of calculus, you convert the given problem, given differential equation, nonlinear differential equation into an equivalent integral equation. This is also nonlinear. So, it is equivalent integral equation. This is the second step. Once this is your established now, the rest of things are very easy. Two things, remember, given problem is there, find appropriate function space, then find the corresponding integral equation, equivalent integral equation. Okay. Now, next step. Now, you convert this integral equation into operator equation. Simple. Just you put the right hand side of this is operator T of x of t. Then this equation is converted into what? Operator equation like this. So, this is operator equation. You consider right hand side to be a operator, T some operator. So, that this equation can be transformed into this operator equation, and solution of this operator equation is the solution of the, because it is equivalent. Since this operator equation is equivalent to this equation, so the solution of that is the solution of this, and solution of this is solution of finish. It is like this. Simple, very simple. How to apply? So, then you will have to show that this operator equation in the space CGR, this is Banach space. Just you show that it is the contraction. If you want to apply Banach contraction principle, just to show, take 2 points. Only 2 points, you consider 2 points like this. Then find this. Find this. So, what you can, this equal to what? Mod here, this get cancelled, x0, equivalent integral equation. So, we will like this. I need not work out the details, it is well known. Because of Lebesgue condition, what to get here? This is equal to, because of Lebesgue condition, we get here total, I write here L A, because it is Lebesgue. Because of Lebesgue condition, we get this relation. And taking the supremum again, what we get here? Over T, take the supremum over T, T over belongs to T over J. So, we get this contraction. So, it is Banach contraction. So, apply Banach contraction principle, very simple. So, convert into integral equation, right hand side is the operator, convert into transform to operator equation, apply Banach contraction principle. This contraction space is complete, it has unique fixed point, and that unique fixed point is the solution of this operator equation. What is the solution? What is the fixed point? Fixed point is the invariant point under this transformation, right? So, this is the fixed point. So, solution means fixed point. So fixed point means solution of this operator equation, and that solution of this operator equation is correspond what it is to the integral equation, and the solution of integral equation is the solution of differential equation. Finish. So simple. How to apply fixed point theorem to? But remember here, it requires a little skill, because depending on the circumstances, differential equation is given. What is the nature of this nonlinear function? You have to first think over it. What is the nature of this nonlinear function? So if it is continuous, say bounded such a Lipschitz condition, then you can apply. Otherwise, you cannot apply. Otherwise, you cannot apply. So again, this theorem fails. Banach quantization maximum fails somewhere. There are certain situations, certain differential equation. So this is not this theorem doesn't work. Banach quantization principle doesn't work. So I have improved that this Banach quantization principle to some here linear quantization is there. So I just here it is okay. It works. Analytic. This is right. So I consider this one more definition, two definition. So D function, I introduce a one D function, which is upper semi-continuous, non-decreasing, and that satisfies psi of 0 equal to. So it is a D function. Making use of this D function, I consider this nonlinear quantization. D Lipschitz, this Lipschitz, definition of D Lipschitz, and if psi of r is less than 1, this is nonlinear D quantization. So it is special of this is quantization. Special of this nonlinear D quantization is this quantization. So there are situations in differential equation where we do not use this Banach quantization principle, but this is useful. These differences theorem is same is if a function t from a complete matrix space into X itself is nonlinear D quantization, then it has a unique fixed point x star, and a sequence of successive iteration goes to the unique fixed point x star. The conclusion is same, but this is slightly improved. That condition is slightly improved. So one paper is a Cubo journal. I approve one theorem. One paper with Grabe and so on. How this is a paper. In that paper, we utilize this particular fixed point theorem. This theorem we have utilized here. So here Banach quantization doesn't work. So this is advantage of this particular theorem. So now see here. What are the conditions? Suppose F doesn't satisfy Lipschitz condition. It is continuous. It is continuous, and then it is bounded. If boundedness is required only for local solution, not for any other solution. If you do not use bounded condition on the function F now, they will get a solution, but not in local solution. So if there is function is continuous and F is also bounded, then another theorem, another fixed point theorem proved by J. Schwader can be applied. Topological fixed point theorem. So all the fixed point theorem on the line of Banach quantization principle is analytical fixed point theory. This is the analytical fixed point theory. That is metric fixed point theory, you may say. Metric fixed point theory. So in midpoint, yeah.
Sir, can you tell about this paper?
Which one? Cubo that published. You can search in Google and.
No, he is asking say something more about this paper.
Yes.
Because it is used in fractional calculus also. So I am interested in this topic also.
Fractional,
Fractional calculus.
we are going away from the topic. Later we shall discuss it, because I am just, so actually in 1 hour it is not possible even we touch to our topic, that hybrid, we can't go. Only just I am explaining the just fundamental application of fixed point theorems or fundamental theorems. So there are very few fixed point theorems in analytic theory, very few, like Banach quantization, such generalization, and other fixed point theorems, they don't have any application. Even famous fixed point theorem proved in I think 1965-67 something, it has no application, and afterward there is no application at all. Only for the sake of entertainment, it's all right. Sometime in future it may have application. I don't claim that none has application. In future it may, those may have application, but so far it is not application. So only few fixed point theorems in analytic theory have applications. So next, let me go to the change the situation. This doesn't satisfy Lipschitz condition. Then does this problem have a solution? Problem. It doesn't satisfy Lipschitz condition. Lipschitz condition is a very strong condition. In nonlinear analysis, this condition is supposed to be very strong. we generally never assume this condition. It's very strong condition. And you know how it is satisfied if this is less than or equal to some constant, it satisfies this condition, Lipschitz condition. That is, you know, all right. But this is very strong condition. Next, if the function is doesn't satisfy this condition, it is continuous and bounded, what happens? Does it have a solution? In that case, the J. Schroeder, Polish mathematician J. Schroeder, he proved one theorem in the infinite dimensional space, named after Schroeder fixed point theorem. So that theorem is useful here in this case. Same procedure. So this same procedure, this is the same procedure. So you have to consider what is that theorem. Theorem is like this. This is topological fixed point theory. So after Schroeder, the first version of this Schroeder fixed point theorem lies in the Brouwer fixed point theorem, which is in final dimensional Banach space. Final dimensional space. This is infinite dimensional Banach space. So he proved that a continuous operator T on a complex convex subset of a S of a Banach space has a fixed point. Simple, very simple. But this theorem is not applicable because it is very difficult to find a complex subset of Banach space. Always, it's not possible. So then this theorem is applicable. It's a modification of this theorem. One and the same little modification. So yes, be a non-closed continuous and bounded subset of Banach space, yeah. And let this is the completely continuous operator. So completely continuous operator means this one. Then it has a fixed point. So this is the famous Schroeder fixed point theorem. Can be applied without Lipschitz condition, only under the assumptions of this continuity and compactness condition. Here in case of R, here total boundedness and continuity enough guaranteeing the compactness of T. But in other cases, it is not true. You have to add some more conditions. So procedure is same. This is same procedure. Now the operator, this equation is converted into operator equation. Up to this, it is all right. Now you show that T is continuous and completely. It shows that it is completely continuous. Completely continuous because continuous plus totally pre-compact or totally boundedness. You have to prove. So for this, you have to make use of the Argyll-Ausclay theorem in Banach spaces. Sometimes if Banach spaces is not real one, then you have to apply that Kolmogorov condition for the compactness. So different. So and for continuity, you have to show dominated convergence theorem. There are so many analysis and this you have to use here, make use of here. You have to use so many analysis. Make use of those results from analysis, you can prove this operator is continuous as well as completely that totally bounded means completely continuous. If and you have to consider one say close continuous and bounded subset of that Banach space. It is very simple to consider. So if you consider like the wall. So this is the integral equation. This is the integral equation. Very simple. This is the equivalent integration to this. Now we consider the ball centered at x0. We consider this ball, and so here R satisfies certain conditions constant. Simple, very simple. So like let us find that R here. So what is the here x of t minus x0? It is equal to mod integral t0 to t mod f is less than equal to yes, like this. Okay, like this, and this is bounded M and here. So it means what? So this is the ball EMA. This is bounded limit of integration from t0 to t0 plus 1. So EMA is a bound. M is a bound. M is the bound of this nonlinear function. So EMA. So you consider open ball centered at x0 of radius r. This r. It is closed, convex, bounded. Every ball, I mean closed ball, is always closed, convex, and bounded. And so show that this operator maps this ball into itself. It is easy to it's very easy. And once we show it maps a closed, convex, bounded subset into itself. Again, you just if you prove that it is continuous and complete and totally bounded by application of this Schroeder fixed point theorem, we get the solution. see here, this is the only Varna contraction principle is the only theorem or its generalization in analysis which gives both existence as well as uniqueness. Short of fixed sum does not give uniqueness, it only gives existence. It has a solution, that's all. Even both the fixed point theorems, from this we don't confirm in fact that this is a solution. This does not provide a solution. Varna contraction principle also does not give the solution. It just approximates the solution, because infinity we don't go up to the infinity, it approximates the solution, and this is the existence. That much we can prove with the help of both this. Solution we never get, because for nonlinear differential equation we don't get the solution. It is like this. Suppose another here we don't get, we do not get the Lipschitz condition, Lipschitz. Only compactness condition is enough. Suppose function is not Lipschitz, again is not even continuous, then the problem has a solution. Again problem. Does this problem have a solution? Function does not satisfy Lipschitz condition. Function is not continuous, not bounded even. Does this problem have a solution or not? This is the second problem. So then another fixed point theorem, Tarski, discrete fixed point theorem. So it doesn't give any continuity, any compactness, any Lipschitz condition. But in that case, so the space under consideration, in which you are placing the problem, this should be complete lattice. This problem is a big problem, because this space, that CGR is not a complete lattice. Many spaces they do not possess this property. Partial, if you introduce a partial order, doesn't always it becomes a lattice. So this is a problem, big problem. But it is lattice. Then you put here condition that this is monotone on x, monotone non-decreasing in the second variable x. It is more, and the procedure is same procedure up to this. So for every application, procedure is common up to this. Up to it is common. Here you just apply that monotonicity of the f, non-linearity of non-linear function, to show that this operator is monotone isolated increasing or monotone non-decreasing, like that. Space is complete, that complete lattice. It has a fixed point. Not only fixed point, it has a maximal fixed point, minimal fixed point. Means it has a minimal solution as well as maximal solution. So additional information you will get. So this is tight position, but additional information you get that the given differential equation has a minimal solution, as well as this additional information you will get from that Tarski fixed point theorem. So this is about your, these are the basic fixed point theorems, fundamental three fixed point theorems of the nonlinear analysis. So two are given by, I think, the Polish mathematician Schroeder and Vanak. I think Tarski from USA. He might be knowing Tarski. Tarski. I have no idea, but he's third fellow from, I think, USA, maybe USA. Maybe. So they are the famous fundamental theorems of the nonlinear analysis. Application like this, right? So my problem now, suppose function is not continuous, does not satisfy this condition, and not monotone. But what can be done? Problem is, does this problem have solution or not? Does this problem have a solution or not? Yes, even then, problem has a solution. But it is just tricky thing. Procedure is same. Procedure is same. Just I explain here. Let me see here whether it is written here something. Oh, is it okay? Yeah. So what is hybrid differential? My problem, my talk is on hybrid differential equation. No? So I have to catch that point. So what is a hybrid differential equation? You know differential equation. You know nonlinear differential equation. Suppose then in case of unaccompanied control principle, F satisfies geometric property, linear, analytic property, Lipschitz condition. Lipschitz condition is metric property. In case of that short of fixed point theorem, it satisfies compactness property, compactness condition, which is topological property. And the algebraic property, in case of Tarski fixed point theorem, there is one algebraic isotone property. We need these three properties for different fixed point theorem. But if F does not possess any property, not Lipschitz, neither continuous nor that we can say monotone, then what can be done? Does this problem has is a problem, and this problem has been settled by that Russian mathematician M.A. Kaspersky. So suppose this is the equation. How to I explain the technical criteria, technicalities of this theorem. So this is the problem. I think okay. This is the differential equation. So selection of fixed point theorem depends upon the situation, circumstances. Remember, in every case we cannot apply all the fixed point theorem. See the circumstances, see the nature of the nonlinear function involved in the differential equation, and depending on that nature of the differential equation, you can consider which fixed point theorem can be applied. So I already told you, good collection of fixed point theorem give you better results. Not only this existence, uniqueness, apart from that, we can discuss other qualitative properties of the differential equation, like the stability of differential equation, attractivity of differential equation, attractivity of two solutions, monotonicity, positivity. So many qualitative properties we can discuss with the help of this fixed point theorem. I also applied all these fixed point theorems in my work. You can go to Google and find my work. So this is the problem. Now F does not satisfy Lipschitz condition, neither nothing like that. What he did, Kaspersky did, so he splitted this function into two components, like this. He splitted this function into two components, like this, in this form. Two components. First component, he split it like this. This is the addition of two components, split it into two components. And where this nonlinear function, first component satisfies Lipschitz condition, second condition satisfies the compactness condition, and then this may have a solution. He proposed and he proved one theorem. That is a I consider it to be a habit. What is first of all I explain what is differential equation. So if this nonlinear function is only one, there may be 2, 3, and so on, no problem. If this nonlinear function or nonlinear functions involved in the differential equation, nonlinear differential equation, possess mixed properties from different branches of mathematics, mixed property, hybrid, that is hybrid, from analysis, algebra, and topology, like this, mixed properties. Then we say it is a hybrid differential equation. Now this becomes, if we split this into this, where F1 satisfies Lipschitz condition, this satisfies compactness condition, then inversion, then it becomes a hybrid differential equation. See, this, which one? This differential is not hybrid differential equation, this is hybrid differential equation. So this is a hybrid, it becomes a hybrid differential equation. Because, so this is a differential equation, this is split into two, subject to same initial condition.
Ravi, you can use different chalk. Different chalk. This chalk. This chalk is better.
Okay.
This is hard.
Okay.
That is a hard. Another one is soft.
So inversion. So this is the differential equation, hybrid differential equation. So what happens? See, novelty of this. What happens here? If you invert this, the inversion of this differential equation gives you sum of two operators like this. F1, F2. So inversion of this differential equation gives rise to this integral equation. Integral equation is the sum of two. You may consider this one operator, and you may consider this to be as second operator. It is two operators. Remember, and he formulated that M.A. Kaspersky Russian mathematician formulated a fixed point theorem involving the sum of two operators like this. So what is his operator equation? So we consider this equation. This is the second equation from the hybrid fixed point theory. Second equation. First equation that one. This is the second equation from hybrid fixed point theory. So he proved a fixed point theorem for this sum of two operators. A is contraction, maybe nonlinear contraction. First of all, he proved only for linear contraction, only contraction. B is completely continuous, compact and continuous, that is completely continuous. Then this operator has a solution. He proved like this. His statement is like this here. In a closed subspace, of course. It's not here, no? Okay.
So, sir, such type differential equations have applications?
Yeah. Number of applications. Usually, so many authors, you read the literature. Of course, whatever I explain here, definitely it has application. So you have to find the physical situation. Physical situation, you find the physical situation. Oh, this is what is the year of this? 1964. Since then, people are working on this problem. Since then, people are working on this problem. Famous problem. Krasnodar fixed problem is famous. So remember that there are 4 parts of nonlinear analysis. Pillar, you may say one building of nonlinear analysis. It is considered to be one building. 4 pillars of this building are this analytic fixed point theory, topological fixed point theory, algebraic fixed point theory, and this hybrid fixed point theory. There are 4 pillars of this building of nonlinear analysis, and both are all are the famous, commonly used here. In 1964, Krasnodar proved this theorem. So its statement is nice. I reproduce here. Let S be a closed, convex, and bounded subset of a one-arc space. It is addition. It is not nonlinear space. So it is one-arc space. Remember here, the theorem is one-arc space. One-arc proved in metric space. So order one-arc. This is one-arc space. So S be a closed, convex, and bounded subset of one-arc space. And there are 2 operators. And let these 2 operators S from. So one-arc space say X make us S from S to X. So no, these 2 operators satisfy 2 conditions. Number 1 condition A is contraction. Second, B, one condition, A condition, B condition. B is completely continuous. And C, this condition must satisfy. Then the hybrid operator equation, it is a hybrid operator equation because 2 operators satisfy different properties for different branches of mathematics. Operator equation Ax plus Bx is equal to Ax. So this has a solution. This is a famous Krasnodar fixed point theorem, proved in 1964. This is 1964. So I just take a few words about this fixed point theorem. Then I will come to that application. So this is the original fixed point theorem proved by Krasnodar. Yeah.
Both operator from the S
Yes, P.S. Yes, P.X. Original fixed point.
You put here C condition Ax plus By. Why not the same point like A plus B of X?
No, Bx what? Ax plus By.
So
X and Y belongs to S.
But maybe it may be something sum of the 2 operator A plus B of X. Why not like sum of the 2 operator condition? But you are
Different, but this is the condition. Maybe outside that set, but this is the condition of that theorem.
So he want to say that Bx हो जाए तो क्या हो? Bx होना चाहिए.
So no. For different positions, it is special. It is a special case. It is 2 different operators. Special case. So this is not Ax plus Bx. Don't consider for different point also.
Is that when we define a sum of the 2 operators, we define like A
Ax
plus B of X.
Yeah.
So that is something
Here like this.
Yeah, that's the
Here,
fixed point.
but this is the condition he has put. Ax plus B for all points X and Y. Addition should be in yes. This is the condition. Later, after some time, Theodore Burton from USA, he improved this condition. Then myself also, improved this theorem a lot. So what I did instead of this, so A and B are, what is this? A and B are from S to X. So A may be some other EM to X, B may be from S to X. It may happen. But in this case, we have to show M is equal to S. This should be, but this is not always the case. This is not case always. So I just extended this restriction. I extended like this. A is from X to X, and B is from S to X. It is like this. And I weaken this condition, this strong, very strong condition. I weaken this condition like this. So X, if X is equal to AX plus BY, implies X belongs to S for all Y belongs to. So I have weakened that condition. This is what a strong condition, and this is applicable everywhere. That theorem is not applicable everywhere, but this is applicable everywhere. So I weaken this. This is extended. This domain is extended, but this condition is restricted. This condition. So this has so many applications. This particular. So here linear contation. This contation linear contation. Here I just replace it by non-linear decontation. Again, so many applications. So I have improved A as well as C, and here extended this like this. So this is a famous theorem. So many applications. In my papers, will find a piece of this. So I procedure said, if there is a differential equation of this kind, so differentiation X dash of t is equal to sum of two operators, sum of two non-linear differential equation. Subject to some initial condition. So whole discussion can be applied to boundary value problems also. This is for the sake of convenience for you and myself. I just IVPs, I use this IVPs, initial value problem. So with initial condition like this. So this is the differential equation. So it is a what is kind of this equation? So actually original equation is that one, A dash U2 F Tx, right? So I have perturbed it, I have splitted it. This is one kind of perturbation. It is called perturbation of linear perturbation of first kind. So all type of perturbation I have given one paper. I have discussed all type of perturbations, modification of this problem. So paper appeared in differential equation applications. So you can see under that Google, you will get that paper. So like this, it is a perturbed differential equation. Perturb, they are original. What is the use of perturbation? You know, if you want to wash some clothes, right? Then you put some soap, something, and then again stir it well. Something. If you add something, you subtract something, you get the solution. Whatever you have, to make the cloth clean. So it is like that. So you add, function is added. Like this. It is splitted out just into two like this, two functions, written like this. So now procedure is same. You convert into equivalent integral equation by using the theory of calculus. Using the theory of calculus, that you will have to use that fundamental theory of calculus. Same procedure, everything is same. You first find the appropriate function space. If this is, if for all t belongs to j, if you write like this now, then solution will be where? Yes. If you put like this is true for almost every t belongs to j. Subject to integration. Where the solution will be? Where the solution lies? You know? Simple. If is not there, you can consider, you can place this problem into CGR. But if this is almost everywhere, you cannot place this problem. Solution does not belong to that space. It belongs to this space. Space of absolute continuous real value function on closed element of j. It is like solution belongs to this. So you have to see where the solution lies. Problem is given. You have to see where the solution lies, and you select appropriate function space, and you place your problem into that, embedded into that function space by selecting some norm. It becomes a one-arc space. Then you just choose this to be 1. So it is equivalent to this one. You choose this operator A, this operator B. This satisfies Lipschitz condition, this compact condition. This is contraction, this is the completely continuous, their operator. And you will have to, one more condition, you have to set this condition, this condition. Take the norm on both sides. This is bounded, this is bounded. So all conditions are satisfied. Hence, you can apply this fixed point theorem. It is a hybrid fixed point theorem from sum of two operators. The first hybrid fixed point theorem among these two is first in this form. So we got a solution, and solution of this is the solution of integral equation, and solution of integral equation is the same as solution of this differential. Proof is finished. A little skill, some computation, nothing else. But you should have some knowledge of the analysis, calculus, all these things, some topology. Topology is very important. Topology. Unless you have topology, the convergence and compactness, how will you understand? You need all the knowledge of all three branches. Then and then we can apply here hybrid fixed point theory. Otherwise, you cannot apply. You first study analytic fixed point theory, topological fixed point theory, that is the algebraic fixed point theory. Then and then only you can go to this hybrid fixed point theory. And hybrid fixed point theory has number of applications. Number of applications, you can prove all other qualitative properties of the solution, stability, asymptotic stability, whatever. There are so many definitions of stability, attractive of solutions, positive solution, whether solution is monotone or not. So many things we can study, discuss. So this is the first hybrid fixed point theory. So local solution also you can prove here, like local solution. So next, second, another. Still people are working this, modifying this condition like this. So another basic fixed point theorem is, it is similar to this, a little different. It is sum of two operators, that is the product of two operators. This is the fixed point theorem correspond to sum of two operators, and that is the product of two operators. Same, but product means we have to discuss in algebra, Banach. We have to go into Banach algebra. In Banach space, you won't get a product like this, right? You have to go into Banach. So theorem is put in Banach algebra. So like this, let S be a closed continuous bounded subset Banach algebra X. X is a Banach algebra. This closed continuous bounded. This is Banach algebra. So what is Banach algebra? You know. So product is well defined, and this norm of this product is less than or equal to norm X into. So it becomes a Banach algebra. So second hybrid fixed point theorem. This is also famous. Many people apply this. Even Professor Lakshmi also applied this one for your information. So same, not much difference. So previously it was like this. Previously it was like this. This is paper is put in Journal of Mathematical Physical Sciences, 1997. Say almost seven, something like that. Something like that. Long back. When I was started work, I worked on this problem in the beginning. So this theorem is proved. So S is a closed continuous and bounded subset of a Banach algebra X, and yes, two operators are from S to X, like this. A is not contraction here; it is Lipschitz with Lipschitz constant. Yale, whatever it may be, Yale or alpha, you may say. Lipschitz constant. It is Lipschitz, not contraction. It is Lipschitz. Second, B is completely continuous, no problem. Third one is, it is completely continuous on S, so bond exists. We write next. So third one is like this: Ax By belongs to S, for all xy belongs to, it's like this. And fourth one, there is one more condition. Here alpha m is less than 1. Where what is the m bond of it exists, supreme of this X belongs to it exists because it is complete, it exists, compact, it exists, the supreme exists. So if these four conditions are satisfied, then operator equation has a solution. Of course, solution is yes, of course, it goes yes. So this is the second fixed point theorem. I have proved in 1997 like this. Have so many applications. I applied in the beginning. I applied to nonlinear integral equation, quadratic integral equation, product of two nonlinearities, integral equation. Then applied to nonlinear differential equation also. I worked with Donald and Reagan. So here he applied Donald Reagan. So here we applied these pixel through differential equations under suitable conditions. So next, I again improve this. Later I improve this. Libjet to this, only phi Libjet with d Libjet. General with d function, I generalize it, improve it, psi, like this. B is completely continuous, and this instead of this. So Ax, if X equal to Ax plus By, implies Ax belongs to S for all Y belongs to S. Of course, this condition is also there. Here condition is modified. So M into for R positive. M is like this. M is equal to norm like this. Second fundamental hybrid fixed function theorem in the analysis, nonlinear function analysis, nonlinear analysis. So I improved first condition from Libjet to d Libjet, generalized, improved. Then this condition is improved. Improved means what here? That domain is extended here like this. B is from S to I. It is like this. Domain is extended. Once domain is extended, we can restrict, we can improve this condition as well as this condition. So first condition is about that d Libjet. Second is complete continuity. So this is the somewhat improved condition like this. And this is the opposite you should satisfy. Under these four conditions, this equation is improvement of previous theorem. Lot of applications, number of applications. It has a solution. So this can be applied for differential equation like this. So this is a hybrid differential equation. I have considered myself Donald Reagan. So initially myself I have investigated this particular differential. Yes.
We are from Ax into Bx is a product.
Product. Yeah, operator. It is one element of this Banach algebra. Ax is one element, Bx element, another element. Banach algebra. Yeah. So Donald Reagan myself applied this fixed function to this equation. Subject to initial condition. Initial problem. So this is the quadratic differential equation. So this is the perturbation of the original differential equation. It is the perturbation of second kind. Quadratic perturbation of second kind means product like this. Quadratic second kind. So if you perturb right hand side, it will be perturbation of first kind. If you perturb left side, perturbation of second kind. It is quadratic. It is not linear. It is quadratic. If product, this is quadratic perturbation. Okay, this is quadratic perturbation of second kind. So this differential equation we have considered, and this paper is published in functional differential equation with Donald Reagan. I think same paper, some modification of that is also published with that R.P. Agrawal, Donald Reagan, and myself in some papers like this. So many papers are there on the problem. So procedure is same. Here remember, instead of Banach's P, here it should be Banach algebra. Remember Banach algebra. So you define suitable norm, right? You find first of all you find what do I mean by solution of the differential equation. Where solution lies. First of all you have to see the space where the solution lies. And then you can decide the space in which this problem should be put or placed like this. Find this particular space. If you place this problem in the particular space, then find the equivalent integral equation, that is usual theory. Using the theory of calculus, you convert this equation into integral equation like this. Procedure is same. Procedure is same. plus same. Like this is the equivalential equation. This operator is A, this operator is B, and show that these two operators satisfy all the conditions of this Habit-Fishman theorem. Second fundamental theorem, Habit-Fishman theorem in the analysis. If these two satisfy all these conditions, then this equation has a solution, integral equation, implies and implied by, so it is the solution of this differential, Habit differential equation. Procedure is very simple. It's not difficult how to apply Fishman theorem and so on. You should have knowledge of calculus thoroughly. Your fractional differential equation, you should have knowledge of fractional calculus and so on. So this is about your two fundamental. What time left? I have not touched my topic. I am interested. We are the builders of Habit-Fishman theory. So this theory is initiated in India. It is India's contribution. Remember, in Fishman analysis, this is India's contribution. There are so many Habit-Fishman theorems from our country proved, you can say, produced. So I am interested in Habit-Fishman theory, but time is limited. I can't go to that my topic. So that particular recent latest Fishman theory. This is old one, latest, very interesting. See, just I will quote one or two sentences about that.
Yeah.
So if the function f is not, say what we can say, Lipschitz, continuous, your algebraic like this, then so there are another type of Habit-Fishman theorems. So this is the topo Habit. These two theorems are topo analytic, means a combination of two arguments from one analysis and one topology. Two arguments. So there are Fishman theorems from one argument from lattice theory, one argument from analysis. Similarly, another one argument from topology, one argument from, and there are four types of Habit-Fishman theorem. So we combine all these three, one argument from analysis, topology, and lattice theory. Very interesting Fishman theorems. Number of applications. So if you are in doubt, you can ask me now and afterwards also. No problem. So time is limited. I am very much thankful to Javed again. So I have a chance to exchange my ideas with Professor Khamsi and all you people. We got inspiration from young people because we expect something from young people. So you follow this line, and I say one problem, simple problem, open problem for you all. So we are in Banach space. Yes is the normative closed canonical subset of Banach space X. You consider this operator equation. You consider three operators, Ax plus Bx plus Cx. These are operators, and find the condition, appropriate condition on A, B, and C, so that this operator equation will have this open problem to you all. Thank you very much for, again I thank Professor Ali Javed, he is my good friend, for giving me an opportunity to speak here.
Thank you very much, Professor Dagi sir. We are still learning from you, and he's no doubt he is very nice work in this area, application of fixed point to differential equation, and of course time is limited, so we cannot go to the latest part.
That part.
But we have one paper with Professor Dagi.
We have said
let us study this one.
Combine that.
So thank you very much, sir, again. And
you can share please in group.
Yeah, of course. उसको बंद कर दो recording, okay? So now it's उसको ले आएंगे हम. So now it's basically lunch break, but lunch will start by 1:15 or 20 because we are Friday today, so we will go some of course not all means we will people go to prayer. So we will assemble here by 1:15, but that time you can enjoy maybe photography or maybe walking here and there, and we will again go through.
I still one of this. Yeah, I remember. वो ऐसे
आपको जामिया में मिले थे.
हाँ अच्छा अच्छा.
सर का एक मैं पेपर फॉलो कर रहा हूँ, वो जावेद सर के साथ है.
ऐसा.
मोनोटोन पे इनका पेपर और संगठन. Mike. He is reading your paper. Sir, he is reading your paper. Hello, hello.
Okay. So, welcome back after the lunch. So, this is the last talk by Professor Ami in this GIAN program. So, it's a tutorial session. So, maybe he will discuss some, maybe some maybe one
I mean,
problem or maybe some.
I want to touch
Stuff,
on some
yes.
stuff. Yes, 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 yes.
So,
So,
so please.
two stuff I want to touch on, which are technical but not in the formal presentation I made, and I wanted to clarify it. One is the minimal convex sets, okay, and how everything that was done depends on the minimal convex set. So I wanna show you something there, and then I want to move to the idea of compactness of the balls. That's very important. The other one is old, 1965, 1975, and so on and so forth. But the one I'm going to be talking about, that's important. I want you to pay attention. So it's more like exercise, more like tutorial than the formal stuff, okay? Than the formal stuff. So let's go first to the first part. So what do we have? We have, okay, let's stay in the 1965 mind. So we have K, which is convex, not empty, subset of a Banach space. And we assume that K is compact. Okay? And we take T, which goes from K to K, which is non-expensive. Okay? If K is reduced to 1 point, then we have fixed point. So of course this problem is interesting if K is not reduced to 1 point. which is equivalent to say that the diam of K is greater than 0. Of course, you may ask me, is it bounded? Yeah, because it's weakly compact. Since it is weakly compact, it is bounded. Okay? So this is the general picture of 1965. Okay? Some people did not go down to K, but that assumed that the space is reflexive. And K is only bounded, closed, convex subset. Okay? So if it is bounded, closed, convex subset, it is weakly compact. From that, from what I am saying right now, came two properties. Okay? Two properties. From this point I'm telling you, came two properties. One is what is known as fixed point property, meaning what? That you have a Banach space for which any bounded, closed, convex subset has the fixed point property for non-expansive mapping. Pay attention. I did not say what? That the space is what? Nor that I said that K is what? Weakly compact. I did not. So what did they say? This is known as what? Did they say weakly fixed point property or fixed point property? What did they say?
Weak fixed point property. Weak fixed point property.
I said weak? Good job. Some people are following me. I meant to lead you to a mistake. But anyway, so if this property I just described is fixed point property. The weak fixed point property, if you assume that K is what? Weakly compact. Now, there is a paper that was published by a student of Brayley, he's an Australian mathematician who is now in Illinois, and his name is Chris Lennard. And Chris Lennard likes always to mislead the people. He's young, by the way, he's not old. And when they talk about fixed point property, if you are not careful, they mean the one for bounded, closed, convex subset. Okay? They don't mean the one for weakly compact, convex subset. These two properties are totally different. So, of course, which one is important to us since 1965 and before? It was the one which is known as weak fixed point property. The problem is many of us do not use weak fixed point property and fixed point property. And therefore, it's mislead the reader if you are not careful. Huh? If you are not careful. Okay. So I'm not going to work with what? With the one for bounded, closed, and convex. I'm working with weak compactness. And the reason is because if I don't have weak compactness, I am not able to generate the minimal invariant set. See? That's the problem. So the proof should be constructive if I'm dealing only with what? With what? With bounded, closed, convex subset. It has to be constructive. You cannot use zone, period. Which takes us to another problem altogether, which is constructive, non-constructive problems. Under what axioms are you working with? Axiom of what? Choice, no, yes. There is all this discussion. Okay? In fact, there was a Turkish student of Kirk who worked his PhD on this. So there is a school of people working on this problem, okay, which is constructive, non-constructive proofs. Okay, so now, what does zone tell us? So if I take the family F of C closed convex subsets of K, not empty, and invariant. Okay? So this family F is not empty because it contains K. Yeah? If I order it ordered by inclusion, okay, and because of weak compactness, then any chain or totally ordered subset of F, the intersection is not empty. That's weak compactness. To be invariant, that's easy because each one of them is invariant. Just set theoretical approach. And therefore, by Zorn lemma, we have what? Minimal element. So here, Zorn lemma applies. Okay? Which gives us what? Minimal elements. Now, this minimal element were used by, what's his name? If you remember the lectures, by Browder in the second paper, not in the first paper. Okay? When he was in Hilbert, it's a different approach. But in the second paper, he used the minimal element, number one. And also, it was used by Kirk. The problem is that in the proof by Browder in the second, it's inherent. He did not know about normal structure property. Nobody knew about normal structure property. And therefore, it was more about what? Kirk, who exhibited the properties, some properties of the minimal element. Okay? Therefore, the main question is, so what is the main problem? And believe me, is the main problem. What are the properties of the minimal elements of F? That's it. 1965, moving forward till today. Some of them are easy to prove, which I will show you in a second. Some of them are not easy to prove, and basically we don't know anything else. When we have information, so let me say, for example, just throw it at you and you will understand where I'm heading with this. Assume that the minimal element is a star. Okay? Assume that we prove that the minimal element, the minimal convex set invariant by T, is a star. Then I have a theorem. If the convex closed sets are not stars in the space, then we have fixed point. Do you see how they approached it? If you give me information on the minimal element, automatically I will give you what? A fixed point theorem. By failing the property that you have there. This will explain two things: the normal structure property and the asymptotic normal structure property, both. Why it took long between the two, I will explain in a second. But basically, that's what it is. So if we know a little bit more about the minimal, it will advance us. How? At understanding the fixed point property. Because the minimal, what does it mean? It's just a set theoretical. Is the least convex, bounded convex set, invariant by T. So you have T, and you have the set. There's nothing else. Except that T, of course, is what? Is non-expansive. Which brings me to another problem altogether, which is AR with ANR. Maybe I'm misleading you. Absolute retract and absolute non-expansive retract. You know what? this would take me completely away from what I want to say, and we don't have time. So let's stick to this. Now, what are the known properties? I will start with A and B I showed you here, and these are the properties that Kirk used in 1965. Okay? So what is the first one? So of course, the problem is interesting if the minimal element is not reduced to what? Because it's invariant. So here we are going to assume what? We assume the minimal element is not reduced. We know it's not empty to one point, because otherwise there is nothing to prove. Okay? So we have C, minimal, T from C to C, minimal. Yeah? The first property was known both to Browder and to Kirk. How? And I showed it to you. So we have T of C included in C. Conv of T of C is included in C, because C is convex and closed. Do we agree? And the conv is the smallest closed convex set which contains the set. Okay? It's the intersection of all of them, in fact. Now, let's take T of that. T of conv of T of C is included in T of C. Yes? And T of C is included in the conv. Yes? Therefore, the conv of TC is invariant. It is closed, convex. Therefore, by minimality of C, by minimality of C, we have C equal conv of TC. Let me make a comment here. I don't want you to take it for granted as being a simple proof. There is something hidden here that is beyond what you saw. The proof is easy, but let us think of it from outside the box, not just to follow the proof and it's a done deal because it's easy. Okay? Does it remind you about Caristia? Huh? Huh? How he got there through steps that are very elementary. But if you think about it outside of the box, it becomes very interesting. It's like opening the door to some big forest. Remember the two trees that hide the big forest? So did you notice here I was just using set theoretical approach? Completely set theoretical approach. Of course, you have to ask me, what is the conv? I used the conv. So once I have the concept of the conv in abstract way, okay, the proof is entirely what? Set theoretical. Are you with me? This comment, I'll come back to it in the second part, okay? Yeah. So this is the first result, that's the famous A in my presentation. That T of C generates C. That is what it means. So C is captured by the image of C by T. So T of C generates C. Okay, now let's go to the second property. This is Kirk now. Huh? Of course, our friend Browder, what did he do? He used uniform convexity to build another set which is invariant with the diameter that is less than the diameter of C. That's what he did. But he never heard of normal structure property. Remember, that was Brodsky-Millman, and Kirk is the one who brought it in force to the people working in Banach spaces. They didn't know about this. So, now, fix X. In C. And let's look at R0, which is basically the Chebyshev radius of X of the set C. I explained it last time, which is basically the sup of the norm x0 minus y, y belongs to C. So this is the radius of the smallest ball, okay, centered at x0, which contains C. That is exactly the meaning. Exactly the meaning. Okay? Is the radius of the smallest ball that contains C centered at x0. Are we in? So far so good? Now, did they use the norm anywhere? Let's go back. So remember what I told you throughout these lectures. It took me 40 years to connect the dot, yes or no? So I don't want you to wait another 40 years, you, to connect the dot. I'm giving you this information so it saves you time. Am I making myself clear? But if I bother you, just tell me, I will move on. Okay. Let me go back. Where do we see the Banach space? Tell me. It's very, very interesting. I can continue with this, keeping an eye on 1965, or even 1975 with Karlovich, but what if I tell you where is exactly the Banach space? And do you understand throughout these lectures why I insist on this? Because my mind is not here. My mind is to try to work with other structures. Like I want to apply this on graph theory, for example. So I mean, it's not a Banach space. So you tell me, where do you see Banach space? I'm serious, by the way. Where? What is the element that uses the Banach space that I need to be careful about? That's what I'm trying to say. What do you think? Tell me. Huh? Yes? Anybody? So we have two spots that we have to be careful about. Spot number one is the weak compactness. Because once you are outside of the Banach space, you need to clarify this problem. Okay? Weak compactness. Is it vital? Yeah, because how am I going to prove the existence of minimal set? Number one. Number two is the conv. I need to pay attention also to the conv. Okay, the closest, smallest convex sets. So these two are there. Okay? What about what you see there? Is that a problem? Tell me about R0. Huh? Is a norm, but that is the distance between x0 and y. Yes? Therefore, I can replace that by what? By the distance. If I have a distance, I'm okay. I'm not using addition of the vectors as well as multiplication by a number. So I'm not using the vector or the linear vector structure of the Banach space. All what I'm telling you are part of these puzzles that you pay attention to them and you spend time reflecting on them, then you connect them. Then you have the big picture. If you don't have that, it's not going to work. You will always stay in generalizing metric spaces and doing contractions. You will never have the big picture. Am I making myself clear? Okay, so what does it mean, this R0? Now let's play with R0. In light of what I just said, let's reinterpret R0. Ready? Huh? Let me show you. So this, in fact, gives me C is included in the ball, closed ball. There is no open ball moving forward. Centered at x0 with radius r0. Do you agree? Yes? Huh? Okay. Now, let's take the image. Is included where? Who wants to tell me? I can't hear you, wallahi, I can't hear you. Tell me. Speak up, don't worry about it. Even if it's wrong, it's okay. Is it in the same bowl? Same bowl? You see? So, T is non-expensive. So, in fact, it's going to be in the bowl, centered x0 with the radius r0. Because T is non-expensive. Huh? T is non-expensive. Yes? Yes? So this opens the door to a new definition of non-expensiveness. So instead of having the distance between tx to ty less than the distance of x to y, if I have a concept of balls, if you give me a concept of balls, then I'm okay. I can define non-expensiveness using what? Balls. It's really crazy. Of course, what's in your mind? Balls means distance. But I can give you a set theoretical approach of balls without a distance. Do you see what I'm trying to do here? Is to open up. Start now to think outside of the box. Everything is up for question. Let's continue. Next. But the balls are convex and they are closed. Therefore, the conv T of C is in that ball. Yes? And what do we know about C? It is equal to the conv. Therefore, it is included in this ball. Now, what does it mean? It means for any y in C, the norm or distance, T of x0 minus y, less than r0, which means the sup of is less than r0. So, if I call this r0 r of x0, r being the Chebyshev radius, what we have here is r of t of x0 is less than r0. Yes? So, let us call now C star the set of all x in C such that the radius is less than r0. Okay? So r of x is the supremum, huh? The Chebyshev radius. R of x is Lipschitzian mapping with constant 1. Therefore, it is continuous. This function is continuous. And it is convex. It's a convex continuous function. Therefore, the set C star is not empty because x0 is there. It is closed. It is convex. You just proved that r of tx is always less than r of x, the proof I showed you, because C is minimal. And therefore, it is invariant. Yeah? So we have what? C star closed. because R is Lipschitzian through the triangle inequality, and convex because R is convex, and T invariant. This gives me what? C star equals C by minimality. What does it mean? It means any x in C, R of x is less than R of x0. Okay. Does this imply R of x is constant? So this conclusion that you see at the bottom, does it imply that the function R of x is constant on C? Because if I take x0 was what? Does it have any special property x0? No. I just took x0. And therefore, this inequality with x0 being what, finally? Arbitrary. So if you have R of x less than R of x0 for any x0 for any x, it means that the function R of x is constant. That's Kirk, not Browder. Browder built another convex by reducing the diameter. Kirk did not do that. He showed, in fact, that R of x is constant. And therefore, so we have R of x constant. But wait a minute. In this case, the supremum, the infimum of R of x are the same. And what is the infimum? Infimum of R of x, x belongs to C. That is the Chebyshev radius of C. And what is the supremum? The supremum of R of x, if you put R of x, is going to be the diameter of C. So what did we found? We found, in fact, that R of C equal diam of C, and the Chebyshev center is the entire set. So this is what's known as C is diametral. When the radius is equal to the diameter, and it's not like, if you take the unit ball in little infinity, it is diametral, the unit ball. Anyway, so now we found the property on the minimal convex set. So we have a new theorem. What is the theorem? If the space does not have what? So we found that the minimal convex sets are diametral. Yes? Therefore, what is the theorem now? We have a new theorem. Okay? If we have a Banach space for which weakly compact convex subsets are what? Non-diametral, we made it. We have a fixed point. That is exactly Kirk's theorem. That is exactly Kirk's theorem. So how? What does that mean, non-diametral? Think about it this way. What does that mean, non-diametral? It means I can find an element in the set such that Rx is strictly less than the diameter. Yes? That's the definition of normal structure property. That's exactly the definition of normal structure property. So the normal structure property tells you only what? That weakly, I'm talking about weakly, of course, normal structure property, because we have this problem between weakly normal structure property and normal structure property. So focus on weakly normal structure property. Okay? It means any weakly compact convex set not reduced to one point has a non-diametral point. That's exactly the definition for normal structure property. Therefore, we found what? Kirk fixed point theorem. That's what it is. Nothing more. So when he put this theorem, people, what is this normal structure property again? Because they never heard of it before. So when they start looking at the normal structure property, it opened a flood of questions about normal structure property in Banach spaces. If you go before 1965, you'll find zero. Nobody worked on it from fixed point theory point of view. Everything started in 1965. Now, we got to a point where people, because anything is related to normal structure property, anything is related to normal structure property. So people started to ask, maybe normal structure property is equivalent to fixed point property. To fixed point property. Equivalent, yeah. I witnessed this. People thought that. 1975. So now Kirk's fixed point theorem, 1965. Now we have to wait in 1975. Okay? People trying. Is there any other property of the minimal set? So we have K, let's say C minimal. Yeah? With diam of C greater than 0, meaning more than 1 point. C is convex, closed, bounded, because it's weakly compact. What did we prove when we started fixed point property in Banach spaces? Do you still remember? If we take a non-expansive map in a Banach space defined on closed, convex, bounded set, non-empty, what did we prove? That's how we started. It was known before 1965 anyway.
We can construct new T epsilon, which is contraction.
Which will lead to what?
One fixed point.
Yes, but it will give us what? Approximate fixed point sequence. So C, so there exists an approximate fixed point sequence xn in C. What does it mean again?
Xn minus Txn.
Good job. Limit xn t of xn equals 0. Yes? Now, let me come up with a new function. Remember the function I used was R. Yes? Now I want to come with a new function. So you tell me. This is Karlovich, by the way. So how would you define? I'll give you a hint, but it gets complicated. So I'm going to define the new function, which is limit norm of xn minus x. And let's call this one phi of x. The problem resides where? Is the limit. What do you mean by limit? Right? Because I didn't say anything about what? About xn. It just belongs to C bounded. So how are you going to define this object? So according to Karlovich, the way he bypassed this problem, he used the Banach limits. Have you heard about this? Okay? You should read about it. Okay? Banach limit. And they write it as lim L I M capital. Banach limit. Are you with me? Now, let's ask my assistant. Let's see if I have the internet here. One second. Do I have the internet? Oh. Why is that? Okay, fine. Just give me a second, and you will see why I'm doing this. Okay. 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 Ready? Tell us, first of all, let me be polite with him. Okay. It's slow, the internet, that's why. If it takes long, I will move on. Ah, hi, how is it going? Okay, good. Good. Enjoying some good time. I always do this, some good time at Aligarh. Okay. Because he needs to know me that I am the one, not somebody else, because my daughter is using it. Okay, now, tell us about Banach limit. Okay? So here he's going to explain to you how to build Banach limit. That's how Banach did it, by the way. Okay? How he came up with the concept of limit. And what's interesting is only for bounded sequences. And what's interesting, it extends the normal limit. So instead of saying there exists a subsequence, you avoid to say that there exists subsequence. Therefore, for my function, I can use Banach limit. I avoid to talk about what? To subsequence. And we know that the Banach limit is always between lim inf and lim sup. Okay? There is another way you can avoid all this, but it's fancy. It's through ultrafilters. Okay? Because in a compact set, sequence in a compact set will always be convergent along an ultrafilter. Okay? Ultrafilter. And therefore, if I use limit over an ultrafilter, again, I can avoid what? The problem of there exists a subsequence, blah, 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 blah. And of course, the third option is to consider the lim sup. Okay? That is also a viable condition to do. Anyway, so let me, and the reason, by the way, the reason I wanted to do this exercise is not to impress you. Oh, no, no, no. No, 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 absolutely not. I'm too old for this. I don't want to impress anybody. It's to encourage you to use what? To use this AI assistant. And don't use the free one. You are not going to get anything with the free one. You need to get the plus. Okay? All my work is done now with this assistant. Okay, so let's go back to our problem. So let's use lim without being precise, huh? Okay? So what do we know about this function? But this function is, again, Lipschitzian mapping with constant 1, therefore it is continuous. Okay? Number 2, it is convex. Number 3, which is far more important, what if I put here t of xn is going to give me the same value. Why? Because xn minus t of xn goes to where? To 0. Okay, so now look at this now. Fix x0. Fix x0 in C. And put R0 equal phi of x0. Yes? And then consider this C star x in C such that phi of x less than R0. Do you see how? Then what happened? C star is going to be convex, closed subset of C. And it's not empty because you have x0 in it. And because of phi of x is less or equal, see, if you put x, okay, let's do it, let's do it. What is phi of x? Lim norm t of x, sorry, t of x equal limit, because it's an approximate fixed point sequence. Yes? And now I can use what? Non-expensive. So phi of t of x is less than phi of x. Therefore, C star is invariant. So what happened? We can use what? Minimal what? Behavior of C to say that C star is equal to C. What does that mean? It means for any x in C, phi of x is less than R0, which is phi of x0. Same argument because x0 was arbitrary anyway. Therefore, the function is what? Constant. The problem is, what is the value? Where are we now? C is weakly compact. I have a sequence xn, therefore, there exists what? A subsequence, which is what? Converges weakly. Let's call omega the weak limit. Using what? The lower semi-continuity of the norm, we get what? That. So, omega, sorry, there exists omega, a weak cluster point of xn. Therefore, omega minus x is going to be less or equal than the limit of the norm of xn minus x. I'm talking about this limit. If you are using an ultrafilter, and because we are in a weakly compact, omega is the limit, the weak limit over the ultrafilter. If you are using the Banach, then any subsequence, the limit over the subsequence will be smaller than the Banach limit. You see, it adjusts, but really it's no big deal. So now, for every x, and this is phi of x, and it's constant. What you have there is phi of x, and phi of x is constant. So this is your phi value. But what is the supremum of omega minus x for x in C? But that's the radius. And we just said what? That is equal to what? The diam. But wait a minute. What is phi again? Is the limit of xn minus x is less than the diam. Therefore, this tells me what? That phi is equal to what? Diam of C. Now, this is Karlovich lemma. Karlovich lemma is telling us that if you take any approximate fixed point sequence in the minimal set, and you take any x in the minimal set, the limit will be exist and is equal to the diam. Okay, we used it from 1975 all the way to 1980 something. Now comes GIAN. And that's why I send you this paper, because it's really beautiful to all of you. What did he see, GIAN? He saw something, honestly, I let it go because I'm not working on this for quite many years, in fact. Many years. Almost 30 years I didn't work on this. But this is what he saw, GIAN. Of course, we used it. Oh, we used this Karlovich lemma, 1975. And I believe it was 19 what? What is it? 1980 what? I forgot. 81? Yeah, check it, check it. Give me the year so it gives you an idea how many years it took. So what did Bayon, Schoenberg, they saw the following. How did we build again the approximate fixed point sequence, Izhar? How?
We can construct with the help of a non-expensive map contraction back, contraction twist.
Okay, how did we build the contraction?
T epsilon.
T epsilon.
81, sir.
19 what?
81, sir.
81. The other name is complicated, Schoenberg, so that's why epsilon z plus 1 minus epsilon t of x. Okay, let's take epsilon. It's a contraction, it has a fixed point. Let's take epsilon equal 1 over n, and xn is the fixed point. Ready? I told you about this anyway. So we have xn equal what? 1 over n z plus 1 minus 1 over n t of xn. And obviously, I showed it to you too during the lectures, that xn minus t of xn goes where? 0 as n goes to infinity. What I did not show you, what did Bayon see, is that in fact, and I leave it to you to do this as an exercise, xn plus 1 minus xn goes to 0. Oh. So it did not just prove that xn is an approximate fixed point sequence. He showed that this sequence satisfies that second condition. Now, what is asymptotic normal structure property? So we have a theorem, new theorem. True. What is it? You assume that if C is invariant, I mean, closed, bounded, convex, weakly compact, T, non-expansive. If xn is an approximate fixed point sequence such that limit xn plus 1 minus xn equals 0, look at now what he did. He assumes there exists an x. Then there exists x in C such that limit of xn minus x less than the diameter. I mean, not only C, and any C, which is T invariant. So he wanted what? To violate what? The property that he discovered. And that's, he called it asymptotic normal property. Asymptotic normal structure property. Let me 2 minutes and I will stop. Now he takes L2, James renorming. What was it? L2 and the new norm, beta positive, I mean bigger than 1. Max, norm 2, beta, norm infinity, soup. Okay? Then, norm beta is bigger, norm 2, less than, beta is bigger than 1. Huh? So otherwise I will put max between 1 and beta. 2. So norm beta is equivalent to norm 2. Is an equivalent norm on the Hilbert space. Why did James come up with this renorming? for beta equals 2. Okay? So for beta equals 2, norm x, I'm sorry, L2 with this new norm fails the normal structure property. Sorry. So the L2 with the new norm fails the normal structure property. Why? Because they said that the normal structure property is satisfied by any reflexive Banach space. What did they tell you? 1965. People did not know about what? About normal structure property. It was brought in by Kirk. And therefore, the people working in Banach spaces, they start asking questions. That's how we do all the time. When we don't know, we start asking questions. So they thought, oh, maybe any reflexive Banach space satisfies the normal structure property. So James told them, James is very famous, by the way. Very famous. Especially James spaces. You should read about this business. So James told them, no, that's not true. And here is a counterexample. How did he thought about it? Don't ask me. It's crazy. Sometimes it's really crazy. Now, what did Bayon do? Bayon showed, and in fact, it was also known that if beta is less than square root of 2, we have normal structure property. Okay? And that was an answer that I answered to Mohammed Amin yesterday, is that you can go all the way, according to Banach-Mazur distance, all the way to square root of 2, and you still have normal structure. You have even uniform normal structure property. Anyway, so what did Bayon do in this paper is that beta between square root of 2 all the way to 2, we don't have normal structure property, but we do have asymptotic normal structure property. That was the essence of that paper. That's exactly the essence. Now, what's amazing in that paper, and finally, again, it's confirmed. I mean, I remember it when I was a student, to be honest with you. That was almost 40 years ago. It's confirmed that for beta equals 2, he proved it. They proved this in that paper, that we have fixed point property, which means that this asymptotic normal structure property is not equivalent to fixed point property. What happened for beta bigger than 2? It says there that Bayon was able to prove for some special values of beta. That he told me himself this. But he was never able to prove it for any beta. So anyway, what's the conclusion? If you can find anything about the minimal set, you have a big theorem. Thank you very much. I wanted to talk about another part, too much. So I want to stop here. I'm going to stop.
Okay, Professor Amin, thank you very much for your this lecture series for the last 4 days.
I will have a PDF for this. I can save it as a PDF and send it to you, okay?
I will share in the group.
Sure.
And of course, he is here with us for tomorrow also. So during the tea break or other time, you can discuss and interact more. So now it's a tea break. So maybe for 15 minutes, and after 15 minutes, so just quickly we will back. And next up by Professor D. Bhavna from IIT Kanpur on differential equations on fixed point. Okay, please.
Thank you, sir. You taught us how to teach. Really excellent.
Okay. So now welcome again to the last talk of the day. And this talk is will be delivered by my postdoc advisor and Professor Bhavna sir from IIT Kanpur. He is very well known in differential equation and of course application of fixed point problems to the theory of differential equation as well as integral equations, control theory, and other related areas. So I welcome sir to the regard and this workshop, and I am very thankful to you. So please you can continue your talk.
So, thank you, Professor Javed, to give me an opportunity to interact with you. So it's after a long time I'm visiting AMU, and it's a good time to, refresh my memories of this place. So you must have, because several talks have already been gone, so you must have already come across what I am going to talk. But I work in differential equations, and very often I use this fixed point theory, and of course the most celebrated one, Banach contraction principle, which is very often is the main tool for many of people who are working in differential equation. Am I audible? Huh? Okay. So I will be delivering two talks here. So first talk is about the this contraction principle and its extension, and then tomorrow I will be talking about its applications, and that will be on differential equations and mostly integral equations, because all those differential equations are then converted to integral equations and then apply the usual fixed point theorems there, whatever is applicable there. Okay, so I will start with the basic that contraction principle, and then talk about its extension today. So as you know, this what do you mean by a fixed point? So you have a certain set X, or let's say you have a space X, and then there is a set M. Usually space will be this X space will be a Banach space, and this M will be a closed subset or subspace of that. So therefore, in its when you restrict the topology of X on M, then it will also be a Banach space, as it is a closed subspace. Okay, so and then there is a map from this space into this M itself. So we call it self map, and we say that a point X in M, if it satisfies this equation that Tx equal to X, we say that X is a fixed point. Okay. And so here the first result in this direction was the this Banach contraction principle. Principle or theorem. But it says that if you have T like this, and here X you can take a metric space also in general. So we will be taking a D rather than the norm of X. So D is a metric there. So you have, if this D of Tx, Ty for any xy in M, if this is less than equal to k times D of xy, where k is strictly less than 1, then we can derive the conclusion that first one is that T has a unique fixed point. Fixed point. We say that fixed point we can denote it by x0. Okay, so that means that is x0 equal to T of x0, and then you start with any x in M and consider the sequence this the sequence T n x, that means you repeatedly apply T on that. So, since it is in, it is a self map, so all these will be in M, and then this converges to x 0. Okay. And third one is that the convergence is uniform if M is bounded. Okay. This with the restriction that M is bounded. Okay. This third can be actually broken into three parts. That is, the first one we will prove all these things, that d of T n x for any x in M, x 0 is less than equal to k to the power n over 1 minus k of d of x dx. Okay, for any x in M and n greater than equal to 1. This 3 1 and also 3 2, that d of T n plus 1 x 0 is less than equal to k over 1 minus k of d of T n plus 1 x T and x, again for each x in M and n greater than equal to 1. Okay. So, in particular we have this rate of convergence, that is d of T n plus 1 x 0 is less than equal to k d of T n x 0. Okay. So, you can see that you repeatedly can go down to T n of x, that is x 1, like you have there, and you get k to the power n there. So, before I give you the proof of this, there was first extension of this, that was the primary extension by Cassi-Pauli, that was Cassiopauli, double P, I think, double P-O-L-I. What it said that if you consider this d of T n x, d of T n y, if there are for each n, if there are these numbers, non-negative numbers, in fact positive numbers, for all x y in M, and such that these CNs are forming the convergent series, okay, then also T has a unique fixed point. In fact, we will show that, you see that because these are convergent, so therefore this is a convergent series, okay, and therefore the nth term will go to 0. Okay. So, nth term there exists some large n such that Cn is strictly less than 1, okay, and therefore for some n this will be a contraction, and we will show that the generalization of this contraction principle, that if for any t, even if it is not even a continuous map, okay, and if for some n, if T n is a contraction, then T has a fixed point. Okay. That also, that is a very powerful generalization, because there see, if it's a contraction, then it has to be continuous. Okay, and this extension, when you have for some n, t to the power n is a contraction, then of course t to the power n becomes continuous, and by this contraction principle it will have a fixed point. Okay, and that implies actually t also has a fixed point. We will establish that also. Okay. So this is the first extension of this famous contraction principle. Now let us look at some examples here also. Tomorrow I will be talking about many more examples. So if you consider this Volterra integral equation, that ux equal to fx plus you have some lambda there, and lambda at the moment you can merge in this kernel kxy and uy dy. So if you of course you have a very standard procedure, you define the iterates like this. So you take maybe u0 of y equal to f u0 of x equal to, or simply as a function f, and then define u1 as u1x as fx plus 0 to x k xy, and then u0, that is, so you write here u0 f whatever u0 y dy, and like that you take the subsequent iterates, that un plus 1x equal to fx plus 0 to x k xy u n y dy. See here ux is unknown because it's appearing here as well as here. Okay, and therefore this is an integral equation. But here each ui's are known because u0 you started with this with a known function, and then u1 is now known. Okay, and so all these are known functions, right? So you generate a sequence. These are and then depending upon the conditions on this, you actually can show that this is a Cauchy sequence, and then therefore if you are considering it in like the function space C, continuous functions or L2 function, L2 space, then if you consider like x as C of let's say if you take it in 0 1 for simplicity, and maybe in complex valued functions, and this is a Banach space, and you if you get these under certain restrictions on this, un going to be a convergent sequence, and that the limit will actually be satisfying the integration. That is one way of approaching this problem. The other way is you look at it as a fixed point problem. So you define that t of ux, or you consider this equation ux equal to f plus or t of ux, which is f plus fx plus this integral operator, we define it as k of u, okay, u of x. What is that integral operator? So here actually we put that lambda here, okay, separately rather than merging it in this, and so you put this lambda here also, okay, and then you consider this t of u1 minus t of u2, okay, so that f will cancel, and you will have lambda, what is that k, actually I did not define, k of u or any function f at x is integral 0 to x, and this k x y f y dy. Okay, for any f, this need not be this f, any, or let's say some g here. Okay, so then this you can see that you get lambda and k of u1 minus k. This is a linear operator, so you can write it as doesn't matter, you can write like this also. And so if you take the norm, then this is less than equal to lambda mod lambda, and then you have this norm k of norm u1 minus norm u2. Okay, these are all L2 norms there, or maybe C norm, or that x, whatever x we take. If you consider this as a space, or we will see that we can generalize it for this one also. Later on we will generalize it for this. At the moment you take this one, and so these are all the supremum norms. Okay, and you see that we will assume that this is going to be a continuous. If you take this as a continuous function, then this k will be a bounded linear operator. Okay, and so you can calculate its norm in fact, and this for a small lambda, this will act like our k. If you write this thing as k, then if you choose for a small lambda, you choose it in such a way that, or this lambda such that mod lambda is less than equal to 1 over norm k, whatever that norm k is there, then you see that this will be a contraction. Okay, so that's another way of looking at this problem, and you see that it will have a unique fixed point, and that fixed point is obviously going to be a solution of this integral equation. Okay, so that is one simple application in this case. Later on tomorrow I will see that how we generalize it for this kind of space also. Now let us look at this contraction theorem and then talk about its various extensions. So let me state that clearly here, this Banach contraction theorem or principle, whatever you call it. So we will do it for a metric space. Let MD be a complete metric space. Completeness is essential here. Metric space, and let T be to N be a contraction. Okay. Then there exists unique x0 in M, such that T of x0 equal to x0, and that was the first thing. And second one is for any x in M, this limit n tends to infinity, Tn of x equal to x0, and then the last one of course, we will see that those 3 different parts of the third one also we will see it separately, but for this in a general setting you have this one as d of T n of x x 0, this is less than equal to k to the power n over 1 minus k d of x T x, or that call it as x 1 will. Okay. Now let us see the proof of this. So since T is a contraction, so you have this d of T x T square x is less than equal to k times d x T x. Okay. Now you add this dx tx you add on both the sides. So what you will have is dx tx plus dtx t square x is less than equal to k dx tx plus k times this one. Okay. So you take it this on this side, so you will have, and then divide it by that one. So you have dx tx is less than equal to 1 over 1 minus k dx. I think I missed, yeah, this one. Did I make a mistake? Okay.
How do you get that k?
1 minute minus. Yeah. Let me see. I think I made a mistake there. 1 minute. Huh? See, this one is okay because you have this is all right. You add this dx tx on both the side, so you have k. Sorry, this. Yeah, this is all right. Okay, that's what I made a mistake there. Okay. Yeah. So now I take it on this side, so I have 1 minus k dx tx is less than equal to dx tx minus dtx t square x. Okay, and then I divide this thing on this other side. I have this 1 over 1 minus k here, 1 over 1 minus k here. Okay, now I define another function psi x, because we will need that. Of course, you don't need this kind of calculations, you can directly do it without that, but since we will need that kind of function later on also, so we take we define a function phi like this, phi from m to this r plus is the non-negative reals. Okay. So by this, that phi of x equal to this side 1 over 1 minus k of only this d of x dx. Okay. You define phi x like this, then this inequality can be written like this, that there is some light problem here. Okay, so then that thing can be written as dx tx is less than equal to this phi of x minus phi of tx. Can be written in this simple fashion. for this is true for any x in M. Okay. Now, so this we can then for a general thing we can write like this: T n x and T m plus 1 x. So what you do is you write T n x T m plus 1 x, and I mean you like this, you write d of T n x and then T m okay. So let me write that and then explain it. So you write this as sum over I equal to n to m d of T I x and T I plus 1 x. Okay. Just adding and subtracting those terms, you keep on doing. Here these are n and m, general n and m. Okay. So T n and T m, here m plus 1. Okay. So then you see that you start with n, and then you get T n and then T n plus 1 here, and by triangle inequality you will keep on writing those things till you end up with the last, that one. So it's a kind of telescopic sum you will have, and which is then each one using this you can write it as phi of T n x minus phi of T m plus 1 x. Okay, is this clear? Because each term you write using what you have done here, okay, using this phi there, okay, and then those intermediate terms will cancel each other, and you will have the first and the last sum. This is called telescopic sum. Okay, so that's what you will have finally. Now here you see that this goes to 0 as m tends to infinity. You keep n fixed and let m tend to infinity, because of that each time you will have k there, and you will keep getting k to the power m at the end. Okay, as n m tends to infinity, k being less than 1, this will go to 0. So you will have, then what you can do is you take n equal to 1 here and let m tend to infinity. So you will have this sum. Then you can write like this, that 1 to infinity d of T I x T of I plus 1 x, which is then less than equal to phi of T x, and which is a finite term. This is strictly less than infinity. Is that so? Here we have this infinite sum of non-negative numbers bounded by this finite quantity. So this is a convergent series. Okay, and therefore its remainder can be made as small as you want. Okay, so by this you can conclude that this T n x is a Cauchy sequence, right? I mean, what do you mean by that? T n x is a Cauchy sequence. Means that what? That anything being Cauchy sequence means what? That for every epsilon greater than 0, there exists some index n, such that for n m greater than equal to this capital N, this d of T n x T m x is less than epsilon. That's what you need to show. Okay, in order to show that this is a Cauchy sequence. Now here, so again you do that here. You let's suppose that this m is bigger. You can without loss of generality, you can take m to be bigger than n. So let's take like that, and then you do the similar thing here. T n and T n minus T n plus 1 and go up to m. Okay, so and so that is you see that will be bounded by, this thing will be then bounded by going I mean little n equal to capital N plus 1 to infinity, right, up to m only first, and then you can, because these non-negative terms, so you can go to infinity, right. So that will be less than this, right. And so since this is a remainder of this convergent series, and therefore can be made as small as you want by choosing this capital N to be large enough. Okay, take any epsilon and then make this quantity to be less than that for any capital N, and then when you choose this n and m, then this quantity is less than that, and therefore it's a Cauchy sequence. Is that clear? And so since this m is complete, and therefore this will converge to a point in that. So that's the first part you have, and then conclude that that is a fixed point. So therefore this limit n tends to infinity Tn of x is some point x0. Okay, now we will show that this is a fixed point. Now here this x0 is actually limit n tends to infinity Tn of x, and that is also limit n tends to infinity of Tn plus 1 x. Okay, because it doesn't matter which point you start, Tn or Tn plus 1, all they are going to right to the same point, right, x0 only. And so now you take that 1t, and being continuous you can take, so you can write it as t of this thing, and t being continuous you can take the limit inside, and so t limit n tends to infinity of x Tn x, and this is x0, so this is t of x0, so x0 equal to tx0. Okay, so this x0 is a fixed point. Now you need to show that this is unique. So let's suppose that y is another element. So suppose that there exists y in M such that t of y equal to y. Now but then this x0, which is actually Tn of limit n tends to infinity Tn of you can start with anything, or let's say, because what happens then, you have Tn of x, and that is also limit n tends to infinity, because what happens, this is so you have t, you keep on applying, this is t to the power n, y will also, this is a constant sequence. Okay, this is a constant sequence, and therefore that will also be going to, you can start with any point we started, and that is going to be Tn of y, which is a constant sequence, and therefore this is equal to y. Okay, so x0 has to be equal to y. Okay, because you, this is showing that you start with any x, it is going to x0. So therefore by this you, same way Tn of y will also go to x0, but this being a this being a fixed point, this is a constant sequence. Each time you apply, because you see ty equal to y, and this t square of y equal to then t of y equal to y. So it's a constant sequence, so it will go to actually y only. So here one thing we are, by this process we are showing that you start with anything, that sequence, when you generate this sequence Tn of x, it goes to x0, and this part we are saying that because of this, that is a constant sequence, and it is actually going to y. Okay. So therefore both the limits must have to be x0. Okay. Now the rate of convergence. Now again we look at that inequality, that d of Tnx Tn plus 1x is less than equal to phi of Tnx minus phi of Tn plus 1 x. Now, so letting n tend this, okay, rather here you have m, I should have phi of Tn plus 1, that was, okay. See, this we had shown that when we defined that phi, we got this inequality, right. So look at that inequality again, and let n be fixed and let m tend to infinity. So then we have okay. So then this will go to x0. So d of Tnx, this is going to x0, and this one was going to 0, and you have Tn of x. But what is phi of Tnx? This is, by definition, it is 1 over 1 minus k of d of the phi of x is what? Phi of x, we recall, that is d of 1 over 1 minus k d of x Tx, right. So for this you have phi of Tnx Tn plus 1 x. Okay. That was one of the those conditions which we needed to prove, and then here you keep on applying that the contraction inequality, you will get k to the power n. So this is less than equal to then k to the power n over 1 minus k d of x Tx. So that is the one we had to finally prove the rate of convergence of that. And then there were other parts like let's recall what were those one. So now if you replace this by Tn plus 1, then you have, okay, so d of or let us say the last one which we wanted to show that d of Tn plus 1, that is more important than this one. This we wanted to show that this is k d of Tnx x0, that is giving you the rate at which it is decreasing. Okay. So here this is same thing as d of Tn plus 1x, but now x0 is a fixed point, and therefore this is equal to T of x, and then you simply get this by the contraction property, you get k of d Tn x x0. Okay. So that proves the thing. Okay. Now, so this is a very powerful result. It not only gives you the fixed point, but also how those are it gives you a way of constructing finding that fixed point also, and how that convergence is actually being reflected. I mean, the rate of this convergence can be seen. So that actually becomes apparent because what that number k is. If k is smaller, of course the rate will be faster. Okay. Now here in most of the applications, when you calculate these, so how you are generating, you have any you starting with any x, and then you are taking this tx as x1, okay, and then xn plus 1 as t of tn of x, right. So when it is 1, you get 1, and okay, tn, I think, all right, tn of x, or yeah, t of let me write it as xn. So this, you have a sequence, either you write it as the sequence xn as tn of something, or you write this sequence xn like this being generated like this, okay, either this one, or you have a sequence tn of x for any x, both are equivalent, okay. So now in many applications these tn or these xn's are not exact the values of t. See, t will be certain operator, and like an integral operator, you may have to numerically calculate those. So you may not be knowing exact value, but certain approximation of that number, okay, or that function. So the important next result is what tells you that how actually even in that approximation it ensures that these errors in your approximation do not grow. That will also converge to the same fixed point. So I will state that and then prove that result. So what you have again, this MD metric space, and T from M to M, it's a contraction, and with the contraction constant. So I mean here this T of x minus T of y, d of T of x, T of y is less than equal to k times d of xy, where k is less than 1. So that contraction constant we are denoting by k. Now supposing that we know that, so therefore there will be a unique fixed point, and let's denote, let x0 be the fixed point, point of t in M, and let a sequence of numbers, positive numbers, epsilons, be a sequence such that this epsilon n is tending to 0 as n tends to infinity. And let's say that y0 is in M and the sequence yn is contained in M, satisfying d of yn plus 1 of t of yn is less than equal to epsilon n for n equal to 1, 2 and so on. So, what it's saying that this t of yn which we are denoting as yn plus 1 is not exactly yn plus 1. By our approximations, our yn plus 1 is close enough to this t of yn, okay, because we are calculating that, and in this process there are some errors being errors creeping in, and but by some way we have an estimate of those errors, and we have that these are less than this epsilon n for each n, okay. And we know that as we keep on approximating, these errors are actually going to 0, okay. Yeah, so you started with the y0 and then you generated that this yns, okay, and this t of yns, but yn plus 1 is not exactly equal to t of yn, but rather kind of approximate. So each time you started y0 and you calculated y1, t of y0, it is not actually equal to y1, but it's an approximation of no, t of y. So y1 is approximation of t of y0, likewise all others, okay. Then we conclude, so this is the thing, then this limit n tends to infinity of yn is actually equal to x0, okay. You started with any y0, and by the Banach contraction principle you know that that sequence has to go to x0, right. But since because of your calculations errors, each time what you are doing, you are not getting exactly, so t of yn is not exactly equal to yn plus 1, but some approximation of that, right. So I mean, then we in general we can't say whether that is yn will go to same point x0 or not, but this theorem ensures that it also will go to that fixed point x0. So in that sense it's a very nice result. Now let us see that.
So space is complete, right?
Yeah. I did not write that. Okay, yeah. This complete metric space. That's a must actually. Sorry. Thanks for complete. Okay.
In this way, sir, we say sequence is stable.
Yeah, it's stable. Yeah, in that. Yeah. Numerical no parlance, it is. You can say that. Okay. So now this proof of this. So we will take that y0 as our any x. So in our earlier terminology, that y0 is any x. Okay, and so then otherwise I don't need to write each time different notations. Okay, so d of then t n m plus 1 x y m plus 1 actually less than equal to, by triangle inequality, d of t m t of t m x, okay, and t of y m, you add and subtract like that, and then by triangle inequality you get t of d of t y m and y m plus 1, okay. And since this is less than by our this condition, it is less than epsilon n. So less than equal to d of so here you can use the contraction thing. So k t of t m of x and y m, and this is plus less than epsilon n. Is that clear? this thing from you have for ym you get epsilon m. Okay, if I have, yeah, n is replaced by m there, and here you take one t out and then apply that. Okay, this you added here like that. Is this clear? So you now
GIAN is not a Picard sequence in this case.
no, it's
It's not a Picard sequence.
no y0. You see, you have y0 and then you take t y0. That should have been y1, but it is not exactly equal to y1. We have some y1 which is close to t of y0 like that. So you're taking slightly, no, I mean it's because of our calculations errors and all. Okay, so that's how you have those sequences there. And now here this can be then you can go down to this last one, and so this you can write then by iteratively you can write this as I equal to 0 to m this k to the power m minus I epsilon I. Okay, so here you have Tm and ym Tm plus 1 ym plus 1, here you Tm ym, and then recursively you go down to that one, and so you each time you will keep on getting these epsilon i's times those k's there, and so this is what you have. Okay, now so by this what you have is d of ym plus 1 x0 is less than equal to d of ym plus 1, again you add and subtract tm plus 1 x plus d of tm plus 1 x x0. Okay, and so this part by our this thing is less than equal to summation I equal to 0 to m k m minus I epsilon I plus d of tm plus 1 x x0. Okay, now let us, this goes to 0, so we don't need to bother about this. Let's look at this one. So that part can be seen like this. So since these epsilon n's are going to 0, so there exists some n such that these for given any epsilon these epsilon given any for any epsilon greater than 0 there exists n like this, such that epsilon n's are less than equal to epsilon for all n greater than equal to capital N. Okay, so then you break this one, and assuming that m is larger than this one, and so I equal to 0 to m k m minus I epsilon I can be written like, you break this sum from I equal to 0 to capital N and then capital N plus 1 to n. So this is equal to summation I equal to 0 to n k epsilon k m minus I epsilon I plus summation n plus 1 I equal to this thing n plus 1 to m, and that is k m minus I epsilon I. Okay, so for these epsilon i's are less than epsilon. Okay, so you can take that out, less than equal to here, and here what you do, you here you write this as k to the power k to the power m minus you take out m minus capital N, and then here you will be left with n minus I. Okay, you take out this k m minus n here, and then n will be here, so it's okay. Now this is something okay, this is a finite sum, some finite quantity, because this is a finite sum only. Okay, and so this is overall it's a finite number, and as little m, this m tends to infinity, this will go to 0. Okay, m being of course larger than capital N, and so k being less than 1, this will go to 0, right? And so therefore, and this you can then take less than equal to n plus 1 to infinity. Okay, and so it will be like 1 over 1 minus k only, right, bounded by that. So you have times epsilon. So this thing is then, so that is going to 0. So as m tends to infinity, this will go, this will be bounded by, as m tends to infinity, what you will get is so limit m tends to infinity of summation I equal to 0 to m k m minus I epsilon I is less than equal to epsilon, and that the larger, that one you will take out up the first term from all, and so you will have, or that sum is actually simply a little this k to the power n plus 1 over 1 minus k. Is that okay? Right? Is this clear? So the first, I mean, that you take out, and then it's like 1 plus k square and so on, and that is 1 over 1 minus k, right? And so again this this is a finite quantity, and so it is bounded by a small quantity, right, epsilon. Since epsilon is arbitrary, so this limit will go to 0. Okay, so that's what we wanted to show, that it will show that because this term is going to 0, right, and this we have shown that this is actually also going to 0. So we finally get that this limit m tends to infinity d of t m plus 1 x x0 equal to 0, and this was nothing but that y0, right? We started with x equal to y0 only, so that's what we wanted to show. Now the next result, which I will be using tomorrow also, is what I talked about in the first extension. That again MD is a complete metric space, and T is from M to M, so that T to the power n, or rather we will write it capital N, T to the power n is a contraction for some n in the natural numbers, then T has a fixed point. So here we have I mean no condition on T, right? Okay, no continuity or anything. No. So by our Banach contraction principle, this Tn has a fixed point. So So, there is some x such that T n of x equal to x. Now, then by this, then you go to T n plus 1, T n plus 1 of x equal to T of T n x equal to, or rather T n of T x equal to T x, right. So, then T x is also a fixed point of T n, right, but T n has a unique fixed point, and therefore, x and T x must be equal, right. So, this implies that by uniqueness of the fixed point of T n implies that this x equal to T x, and therefore, x is a fixed point of T. Is that clear? It is a very simple proof, but it is quite powerful, as you will see tomorrow. That is what we are going to use. Now, there are many extensions of these results. So, one would like to see, can we relax this contraction condition, like if this result has relaxed contraction condition, in fact. So, in more general sense, its answer is no, but there are under certain additional conditions you will have, other than this result you have. Of course, here is the additional condition is that T to the power, there has to have some n like this, where T to the power n is a contraction. That is also quite a restriction on that in some sense. So, the next class of these conditions, what you call is contractive conditions. So, even for that, the result is not in general true. Okay, you need some additional requirements. So, let us see that result first, and then talk about that contractive conditions and many results, many extensions using that. So, this example is, you just relax a bit. What is a contractive condition? That d of Tx and Ty is strictly less than d of x y for x not equal to 1. Okay, because if x equal to y, then this is going to be 0. This of course is also 0. So, a strict inequality cannot be there. So, this condition is meaningful only for x not equal to y. So, it is called contractive condition. T is called contractive. See, if it is a contraction, then you have some k there or alpha, whatever you call, and that alpha is less than 1. But in this case, it is 1 here, and so this is actually called contractive. That is called contraction, and it is called contractive. Okay. So, let us look at this example. That in this case, in general, you will not have a fixed point. You need certain additional requirements. So, you consider, let us say, m equal to, in this case, is C01. And you consider this m, rather this set m, set of all f in this, such that f of 1 equal to 1. Okay. So, elements in this are continuous functions on 0, 1, such that f of 1 equal to 1. Okay. That is the requirement, additional requirement for this m. Now, and define this T from m to m by this, that T of f at T equal to TFT, the multiplication operator for any T in 0, 1. now we will show that this is a contractive map, but it does not have any fixed point. Okay. So, this condition does not guarantee a fixed point, like that contraction theorem, you have always a unique fixed point. So, if you relax it a little bit like that, you do not guarantee, you do not have a fixed point. Now, how do we prove that? So, let us take so here if you look at this T for any Fn G in M. So, what is Tf minus Tg, Tf at T minus Tg at T.
Sir, you can skip this one, we already discussed this.
Achha, this example you discussed, okay, then fine.
Fortunately, this is in the maybe 2 days.
Okay, okay, yeah, that's a nice example.
Nice
Yeah. Okay, so you know it. Okay, so let's look at then the other result.
Okay. State, then we can stop.
Yeah, okay. So, okay, we'll then skip this part. Okay, so then now first then when does this guarantee, what is that additional condition? The first result is that M is actually a compact metric space. Okay, so that is the result, that this MD be a compact metric space, and T from M to M be contractive, then T has a fixed point. T has a fixed point. And also fixed point, unique fixed point. T has a unique. Of course, whenever contract condition is, fixed point is unique, that you can easily see. So, unique fixed point, moreover, and you have this limit n tends to infinity, T n of x equal to x 0. Okay. So, here we define a similar map like we defined phi, we define psi because we get rid of that denominator here and consider only that. So, proof of this is very simple 2-step proof. So, I will finish this and then stop. So, you define psi of x equal to d of x t x. See, earlier we had 1 over 1 minus k there, so we will give another notation psi x here. So, then psi of t x 0 is d of t x 0 t square x 0 . One thing is actually this because it's a contractive thing. So, this let's look at first. Okay. One thing, this psi is actually it's a continuous map because D is a continuous map, right, distance function, and it is bounded below, and because of okay, what is I missing? Okay, psi is continuous and bounded below, so it will assume a minimum. So, let us take psi of x 0 be minimum of psi of x on x belonging to M. Okay. Now, if t of x 0 is not equal to x 0, supposing that x 0 If T of x0 is x0, then we are done. And suppose that this is not. Then you look at these things. Then you have this as okay. Yeah. Since okay, because t square. Okay. Now this is simply less than equal less than 1 minute less than d of x0 t of x0. Okay. Now so this is now psi of okay psi of x0. By definition it is psi of x0. Is this clear? Psi of tx0 is this, and because here there is a contractive condition, these again you have this is not equal to this, and then you get these things like this, and this is equal to psi of x0. Because if this is equal to this, then again you get a fixed point. So assuming that is not, you get this, and psi this is equal to psi of x0. Okay, but psi of x0 is minimum. So but you are getting t of x0 another point, since it is not equal to x0, which is less than, which is a contradiction. Okay, so you actually cannot have this, and therefore this cannot be possible. So this has to be a fixed point. Now only thing that limit thing is what is required to prove. So do I have time or to prove it? Huh?
Proof we already.
Acha, you already. Okay.
Understood theorem.
Okay. Huh. Yeah. Okay.
So maybe you can skip.
So I'll stop here then. Okay. If you have any questions, otherwise. Okay.
Thank you very much, sir. If you have any query and question, then you can ask here.
So interesting part will be tomorrow, where I'll actually demonstrate how powerful these results are.
Part. So tomorrow is the first talk by the Bhavna sir. So don't skip that talk, because that is totally different when it goes. So maybe you can touch some semi-group of linear operator technique. Just some part only adjustment, and maybe.
Let's see how. Actually, I have a different plan, but let's see whatever I can.
So you have 1.5 hours tomorrow. So. So